All right. So today we're here. We're 8:10. We basically have this week and next week, and then we're done, which seems fast, but I'm not overly surprised that the semester's end is at hand. So we are covering climate change. A couple things just to sort of keep your eye on. There's a documentary for you guys to watch. You could just Google Before the Flood. It's available free pretty much everywhere. It stars Leonardo DiCaprio, so the gentleman that you guys probably all know from awesome movies like Inception and stuff like that. It's a pretty good little documentary. It was really I've showed it every year for about 5 years now, since it came out pretty much, and it was great. It was great for like, I don't know what, like 3 years, and then we immediately pulled out of the Paris Climate Agreement, and so it was kind of a sad documentary show because it's like this cool documentary. He's like, oh, here's the Paris Climate Accord, blah blah blah, and then we're just not in it anymore. But thankfully, we've gotten back into the climate accord, the Paris Climate Accord, of course. So it's a much better documentary to watch. Just as a note. So definitely take a peek at it. It's about 90 minutes or so, but we'll cover all the topics we're going to cover today. But it'll be narrated by Leonardo DiCaprio, so it'll be much better. It's not like it's narrated by like David Attenborough, who's arguably one of the best narrators out there, but still probably better than listening to this face. So. In terms of other things to keep your eye on, you have a backyard biodiversity lab that is due today. So if you haven't done that, please make sure you do it. And then we just have sort of three last things to take care of. We have podcasts, discussion board, your final one. It's due the 17th. So you got about a week to do it. There we have a short lab. We sort of already discussed this lab last time we were together, but it's on plastics, about bioaccumulation. There's a documentary involved, so definitely don't save it for the last minute because you need materials, right? You have to buy iodine, and I've answered a few questions about what type of iodine is okay. Just as long as there's iodine on it, you're a-okay. Just to let you know. And then the final thing is going to be our exam. So we'll have a little review session here. I know it doesn't say it on the thing. I guess I just forgot to put it in here, but we'll have a little review sesh the 17th together, and then we'll have your exam. I'm thinking about making it more multiple choice this time, just so it'll be shorter for everyone, but I haven't decided yet. So you'll know more about your exam on the 17th. So, yep, you had a question, Katerina?
So I sent an email about this a little while ago, but I just wanted to see if other people in the class are also having the same issue, that if you're part of a group and you weren't the group member who posted the lab, if you're not seeing the grade for it, because it's still not coming up on my Blackboard.
Okay, I'll take a peek at it. I'll have to take a peek at it. I could just manually enter the grade for you. So I'll take a peek at that today. I know you had emailed me about that. Apparently I just forgot to do it. So I'll take a peek at it after we're done in class today. Just make sure everyone has your grades. I mean, you're not gonna get 0 for it or anything like that. So don't worry about it. I checked the grade book before I submit all your grades and stuff like that. So definitely don't worry about it. I'll go through and adjust things, make sure everything's a-okay for you guys. I always tell students, if I make a mistake and I give you too many points, never tell me. But if I don't give you enough points, always just hit me with a newspaper till I actually give you your points. So I'll take care of that today. Let me just quickly jot that down, just because otherwise I'll probably forget again. So just give me 1 second. Hopefully I can read that. I was at the grocery store yesterday with my wife, and I walked around the store for 30 minutes trying to figure out 2 items that I needed because I couldn't read my own handwriting. All right, check. I can read that. That's check. Okay, good. Handwriting is so bad. Let's see, guys. So you're lucky you don't have you only see me type things out. So Chippy. Okay. So if you have any questions about grading or assignments or anything, definitely let me know. But let's dive into it. We got a doozy to go through today. It's a really sizable topic. So let's get into it. Let me just stop my video for quality, and let's go into it. So climate change. It's been around for a long time. this concept. So the idea of climate change actually started in the 20s, sort of something not a lot of people know. We sort of think about it as more of a 20th century, 21st century sort of, late 20th, early 21st century sort of idea. But climate change as a scientific idea has actually been on a lot of people's minds for about 100 years now. And as time progresses, it becomes sort of a more and more dire sort of state. And there was a recent report that came out really highlighting how dire of a state we're in. But we'll talk about that. We'll talk about that later. But let's talk about the sort of overall ideas of climate change, and we'll start off with a little cartoon of this guy. He's sweating because he's looking in his mirror, and it says objects in the mirror are closer than they appear. I'm sure you guys have all seen that. You probably all drive. And he sees in that mirror, you got this bald-headed dude called global warming running at this guy. And so he's scared of global warming because it's closer than it appears. And I like to start off with this comic, and I've used this comic for years. And simply because, I mean, it's not super funny or anything like that, but it really is super accurate. We sort of have always viewed climate change as a down the road problem, right? Let's kick the can on the idea. But the reality is it is closer than it appears, whether it's the wildfires in California, whether it's droughts here in Massachusetts, whether it's extreme heat in, say, the Middle East. All these effects that we're seeing on our sort of daily lives are climate change right now. And the final thing I'll make mention of is it says global warming. Global warming is not a term scientists use really any longer. It's really, and as you'll see why this is the case, but it's really climate change as opposed to global warming. And again, you'll see why that's the case in a few short slides. So when I'm talking about climate change, I always like to go local. Now, when I was your age, I worked in a pizza shop. I lived in Quincy, and I was working at Milton House of Pizza. Milton, Massachusetts is the town right next to Quincy, and I worked in this pizza shop while I was your age. I was going to school for biology, and I had this customer who just really liked to talk about like conspiracy theories all the time. It was this older gentleman, and this older guy. He was just like, he would come and he would order the same thing every time, and he would talk about conspiracy theories. And it was kind of interesting to listen to him talk about UFOs and stuff like that. But being a biologist, when he started talking about why climate change is a hoax and why climate change isn't real, I just couldn't help myself. So my response to him when he would talk about climate change is like, have you look at the records of this place that I'm showing you guys. Now, we have two pictures here, pretty awesome little piece of scenery here, some nice fall leaves, as New England likes to do. And then we have this tower looking thing here. Does anybody recognize, in particular, this tower? You probably don't recognize the view because it's kind of an arbitrary view. But does anybody recognize this little tower?
Is that Blue Hills?
Exacto. Yeah, so that's the Blue Hills Observatory. For those guys who don't know about the Blue Hills Reservation, it's just south of Boston. It's in Milton, Braintree, Quincy, and Randolph. It's a really nice little, pristine area, just nestled beneath Boston. Now, they're just a bunch of hills. They're not mountains, so they're not particularly very tough of a hike. However, they're nice, right? It's a nice little habitat. People have been going there for years and years and years. And on top of the largest hill, which is called Big Blue Hill, which I think is aptly named, they have a weather observatory. And that weather observatory, as you can tell, is quite old. And it's actually been cranking along since the 1850s. And so my little conspiracy theory friend at the pizza shop that I was just mentioning, I would always tell him to go find this graph. I would tell him to go look at the temperature data at the Blue Hills Observatory because he was from Milton. He lived in Milton and he was all about Milton. So he knew all about the Blue Hill Observatory. And once he finally looked it up, he actually finally stopped actually mentioning climate change and global warming as a whole thing to me, which was kind of nice. Because when you look at this data, which is simply the annual temperature data from 1830 to 2017, temperatures in degrees centigrade and temperature in degrees Fahrenheit on the side, they're two sides of the same coin, of course. Black line is our yearly temperature measurements. Blue line and red line represent 10 and 30-year means respectively. And you can see the data goes from about the 1830s all the way up to 2017. So why did this graph, when you physically look at it, what do you see? And why would it be a good graph to show someone like my pizza shop friend? I wouldn't really consider him my friend, but why is it, what do you see? What sorts of patterns jump out to you guys? You can drop it in the chat. You can say it. I don't really care.
So it seems kind of obvious, but like the temperatures just is increasing, but also like Pio said in the chat, it's a rising trend, but also you can see like from year to year it goes up and then down and then up. Like it doesn't, it continuously goes up, but it keeps going up and down, if that makes sense.
Yeah, it looks like a heart monitor, right? That, like, you guys have seen like House or Grey's Anatomy, right? You look at a heart monitor, that's what it looks like. So the yearly temperature values look like a heart monitor, and you see it just consistently going up and up and up. So those are the really two things you should take away from this graph. Probably the only two things you can take away from this graph as a matter of fact. But yeah, guys did a great job. I usually have to mention what the black line is doing, but you guys got both of them, so I'm very proud of you. But yeah, the trend is pretty dang clear. Since the 1800s, we're seeing a steady increase in temperature, which in Massachusetts, we're at least on top of the Big Blue Hill from 1850. So you guys probably remember this is about the time the Industrial Revolution really kicked into full gear, right? The 1800s, textile industry was going crazy, right? Coal power, steam powered ships, right? That's when things were really ramping up in this area, right? Era, I should say. And then by the time of the 1900s, we start to see that steady rise in temperature from about 7.5 degrees, we'll say, all the way up to about 10 degrees or so in modern times. So that's what we're seeing in the Blue Hills. We're seeing a steady increase. And the other thing you make mention of is that it's variable. And I think sort of some of these points show it pretty easily, right? 8 degrees here. A few years later, it's down to 6.5 or 6.25, right? It's pretty dynamic. So again, the two things you want to take away: long-term changes in temperature, but temperature is variable from year to year to year. And we'll talk about why that sort of is, why like one shows one thing and the other shows some slightly different. But this pattern we're seeing at the Blue Hills, you can look at any weather observatory on the planet. You can look at one in Dubai, you can look at one in Madrid, Beijing, Sydney, anywhere around the world that you can think of that has long-term weather observations. You see this pattern. Year-to-year variability, which is pretty cool, but long-term increase in temperature, both at the local level and the global level. So that's the phenomenon we're going to talk about today. What the heck drives this? You guys probably already have an idea, but we're going to talk about the concrete science behind this idea. So our agenda for today is multifaceted. So it's going to be about 2 hours. 2 hours and 15 minutes or so. So it's a beefy class. Usually we talk about water and then we talk about air, and each of those is about 40 minutes. This one is 2 hours on one single topic. So it's quite a bit. But you'll notice we cover a lot of stuff, right? We'll cover climate, we'll cover the atmosphere, which we've talked about a little bit, but we'll talk about it in particular through the lens of the composition of the atmosphere. Now, then we'll talk about how the Earth is warmed, and the greenhouse effect. Then we'll talk about a 800,000-year look at the Earth's climate, which is, I think, pretty dang cool. And then we'll talk about how humans factor into climate change. And then we'll talk about the impacts of climate change. And then we'll spend a little bit of time talking about feedback loops. We'll talk about some ethical issues. And then I'll end with sort of a really, what I think a really powerful sort of quote, a little powerful speech I heard a few years ago about climate change. So let's dive in. So we'll start with climate versus weather. This is a common misconception about climate change as a topic, right? I can go out today in my backyard. It's humid, but it's, it's 80s. That's what it's supposed to be in the summer. But if it was 70, say if it was 65 degrees tomorrow, right? That's that dramatic change on a day-to-day or potentially a week-to-week basis is our weather, right? And so weather as a construct, as you guys probably know, encompasses a lot of different things: wind, humidity, precipitation, how much solar radiation there is, temperature, cloudiness, et cetera, et cetera. And it, again, is over short periods of time. So if we just jump back 2 slides, this black line more closely represents weather, short-term changes in temperature, short-term changes in precipitation, and so on and so forth. Whereas climate while it does encompass weather, it simply looks at those long-term trends. So this blue line, this red line, that's our climate, right? Long-term trends. And when you turn on the weather channel, you fire up your weather app on your phone or whatever. When you look at, oh, it's going to be 90 degrees and humid tomorrow, that's our weather, right? The top map here is our weather, right? And that's really what we're seeing, right? What is the conditions today, right? And then we have our climate, which is sort of our long-term patterns, right? Oh, it's considerably dry in the American Southwest from year to year to year to year, and it's been that way for a long time. Or it's consistently rainy in Seattle, right? Or it's consistently snowy in the Arctic Circle, right? Those long-term consistent patterns, that's our friend climate. And that is what's changing. The weather changes, and the weather changes for a lot of reasons, as we discussed, but the long-term changes in climate are what's really, really worrying us. And sort of the final thing I'll make mention, and just a really nice quote. So Mark Twain has a really nice quote where Mark Twain says, "The climate is what you expect, the weather is what you get." And Mark Twain is obviously way better with words than I am. So I think that quote really encompasses the difference between climate and weather. So let's go back to our atmosphere, because this is going to play a really important role in today. Now, remember, our atmosphere, it's not exactly the largest thing on the planet, right? You can hop in a car, drive directly northward directly vertically, and if you drove at 60 miles an hour, you would be in outer space, right? So when Elon, what's his face, Jeff Bezos and that other dude went up to space, right? They were in the 60-mile or so range, right? So it's not a lot of sort of distance between the surface of Earth and space, which I always sort of boggles my mind. But this is our atmosphere. You guys will recognize this picture. It's a bit different than the one I showed you, but it shows you the same thing, right? Where we have all these different layers, different things happen in them, right? But the sort of the most important areas, in particular with respect to climate, is actually these two layers. So the first is going to be the ozone layer, and we'll talk about the ozone layer in a few slides, but keep it in the back of your head. It's nestled about 20 to 30 kilometers up in the stratosphere. And then we have the troposphere. And as we sort of mentioned in the class about air, pretty much all the good stuff, weather, and all the things that you've ever done in your life have occurred in the troposphere. Very rarely do you ever leave the troposphere, just the way it is. So keep in mind, we're thinking mostly about the troposphere. We'll talk a little bit about the stratosphere, but pretty much all we're talking about is the troposphere, because that's where all the action is happening. Now, the atmosphere is remarkably consistent. And the kind of the cool thing about the atmosphere, wish I had a picture of the planet or something here, but I don't. No matter where you go on the planet, if you go to China or you go to Hawaii, the atmosphere is essentially exactly the same. So the composition of gas in one area of the planet is pretty much identical to the other part of the planet, which is pretty cool. So let's talk about those gases. So what are the normal gases? What does our atmosphere normally look like? Well, it's 78% nitrogen. Nitrogen is really, really important for lots of things, but the nitrogen in our atmosphere, it basically does nothing. It's basically inert. It just kind of hangs around there. And that's what most of our atmosphere is, nitrogen. So it's not a particularly spectacular thing, but it's hanging around there doing nitrogen stuff. Now, the next biggest gas is our beloved friend, oxygen, at 21%. So you'll notice that oxygen, which plants produce, right, which we need to survive, paired with nitrogen, is 99% of our atmosphere, which I don't know. Maybe it's not so exciting to you, but I remember when I first learned that when I was younger, I was like, wow, that is remarkably simple. Despite how sort of dynamic the atmosphere is, it is remarkably simple. Two gases, 99%. Now, the 1% of those gases are actually where sort of interesting things start to happen. Now, what are some of those other gases? What is that less than 1%? Well, the most common gas in that less than 1% is actually a gas called argon. It's what's called a noble gas. It's very much like nitrogen. It just kind of hangs around and does nothing. It's basically inert. So argon is about 0.8 to 0.9% of the atmosphere at times. And then the other major gas in that less than 1% is actually carbon dioxide. Carbon dioxide is not nearly as abundant as argon, but it's certainly an important feature of our atmosphere, and you'll see why in just a moment. And there are a bunch of other gases up there. And we'll talk about a few of them, but there's a lot of gases up there that comprise that less than 1%, but they're very, very small quantity-wise of our atmosphere. Now, the other important part of our atmosphere is actually water vapor. Now, water vapor comprises 0 to 4%. It varies pretty heavily depending on where you are in the planet. So the tropics have much, much more water vapor in the atmosphere than, say, the Antarctic does. So water vapor, as we'll discuss, varies depending on temperature. So that's our atmosphere. Again, remarkably simple, which is good and bad. It's good because it makes it easy to study, right? And I don't really think there's any bad reasons, but it is good because it makes it relatively easy to study. Now, one aspect of our atmosphere, which is again in the stratosphere, is a layer called the ozone layer. Now, we've discussed the ozone layer a little bit, but I like to leave the ozone layer mostly when I talk about climate change, because there's an important myth surrounding climate change tied to the ozone layer that I have to dispel. Now, ozone, it's O3. It's a super duper important gas, but it's a very, very thin layer of gas around our atmosphere. Now, the ozone layer is pretty dang important. If it wasn't for the ozone layer, life on the surface of the planet simply could not exist. Now, why is that? Well, the ozone layer, as I mentioned earlier in the semester, blocks the vast majority of ultraviolet light. Ultraviolet light actually has 3 distinct types: UVA, UVB, and UVC. UVC is by far the most damaging of all the UV light out there, and it actually simply is completely blocked by our ozone layer. So our ozone layer is pretty awesome. It protects you from the most damaging type of ultraviolet light. Then we have UVA and UVB. A very small proportion of UVB actually makes it to the surface. The ozone layer does a pretty good job of keeping it in check. And then most of, if not all of UVA makes it down to the surface of the Earth. But again, UVC is the bad boy. UVB is bad, but not even close to being as bad as UVC. And UVA, while still bad, not as bad as UVC. So our ozone layer protects us from ultraviolet light. And you might think of, well, why do I care about ultraviolet light? Well, if you're like me, you guys have seen my face looks like. You guys know I'm pale because I'm just a white boy from Boston. I care about the sun all the time because I'm very, very pale. I get sunburned very easily, but I don't really care about the sunburn aspect, even though sunburns really suck. I really care about the ultraviolet light, because what ultraviolet light is, it's a mutagen. It damages your DNA. And so if you get exposed to a lot of ultraviolet light, whether it's through the sun, whether it's through a tanning bed, you potentially damage your DNA. And as you guys probably all know, damage to DNA leads to some pretty severe things like cancer and other types of disorders. So our ozone layer is super duper important. It makes life on land habitable. Life would still exist in the ocean, just as a note, because UV light doesn't penetrate more than, I think, about 2.5 feet, if I'm not mistaken, into the ocean. So the ocean would be fine, but we certainly wouldn't have cool things like giraffes and obviously humans. So ozone layer, super important for biological life. However, like pretty much everything on this planet, we've destroyed our ozone layer in some shape or form. That's just sort of the things humans do, right? That's the hallmark of the Anthropocene, right? We used to have awesome saber-toothed tigers and woolly mammoths and giant sloths here in North America, and the Anthropocene got rid of those things on us, right? So it's kind of a trademark of the Anthropocene, right? But the big destroyer of the ozone historically has actually been a type of gas called CFCs, or chlorofluorocarbons. It's a tough one to say 5 times fast. And these gases are actually produced as to be part of refrigerants, air conditioners, things like that. They're really good at their job. They're fantastic, actually. But when people would throw out air conditioners and refrigerators and stuff like that, these gases, these CFCs, will get into the atmosphere. They would get into the ozone layer, react with the ozone layer, and just start destroying ozone, getting rid of ozone, which, given how important it is for protecting us, you can imagine any damage to the ozone layer is kind of a bad thing. And you'd be right. So much so that we started observing large holes in the ozone layer over the Antarctic Circle. So down under, right? And they were substantial. They were huge. Like, these ozone layers holes were huge. I mean, you could see this is about 20% of the planet. We had a monstrous ozone hole in the Antarctic. So to solve this problem, we actually set up the Montreal Protocol in 1987, so long before you guys were born, and actually before I was born, as a matter of fact. And actually, what this protocol did, it was a global protocol, and it actually set forth essentially the stoppage of the use of these gases that destroyed our ozone layers within about 5 to 10 years. Now you can sort of see this in 1995, so 8 years after the Montreal Protocol, and you notice over time the holes get they get smaller, right? I mean the blue is still there certainly, but the red is getting less deep, and then you sort of see it creeping back every now and then. And so these graphs might not instill a ton of confidence about how effective the ozone, how effective this protocol was, but it actually was really, really, really effective. It actually reduced ozone holes by about 80%. So this one protocol signed by all industrialized nations on the planet saved our ozone layer. But again, you can sort of see it's creeping back. And actually, if you look at maps of the ozone layer right now, it's actually in a pretty not so awesome state. So we'll talk about why that is soon. But just to know, the Montreal Protocol was very successful at limiting how much we destroyed our ozone layer. And the sort of the important thing about the Montreal Protocol is it was accurate, and it worked really well, but it was based on really good science, and people adhered to it. And so it really shows how we can come together globally to fix a global problem. And we did it in a couple of years, which is really, really fantastic when you sort of think about how difficult it is to do anything, let alone within a single country, but at the global level, right? So the Montreal Protocol is awesome. If you want to read about the Montreal Protocol, take a peek at this. And there's also some links here for you as well, one from the EPA and one from NASA, for you guys to learn a little bit more about that if anything I said interests you. Now, there's an important myth surrounding ozone. Now, people have made the claim falsely, I'll just put that out there right this second, that any damage to the ozone layer that we've caused actually has been leading to climate change. And this is simply just not true. Now, why is this not true? Well, when we think about the sun's rays are comprised of many different types of what we call electromagnetic radiation. That's just a fancy word of just saying just types of energy. That's really all it is. Now, of all those parts of the sun's rays, that come to planet Earth, ultraviolet light is actually, while a decent component, is actually relatively rare relative to what we would call the thermal radiation of Earth, right? The light from the sun that you can see, the light that actually warms the planet. And so while ultraviolet light certainly comes here from the sun, and it's certainly absorbed by the ozone layer, the reality is ultraviolet light plays such a minute role in the heating of the planet that even if we got rid of the ozone layer altogether, it wouldn't raise the Earth temperature by more than a fraction of a percent. So again, the ozone layer is in trouble, and that's concerning for a lot of reasons, but it simply does not play a role in climate change, does not whatsoever. So just dispelling one common myth you'll see on the internet that the hole in the ozone layer is why climate change is a thing. It's just simply not true. The ozone layer does great things for protecting us against UV, but just because it blocks UV or lets more UV in, it simply doesn't influence how warm our planet is getting. So if you ever hear anyone say that, you show them these slides and you matumbo them and you go, no, So, okay, so that's our friend, the ozone layer. That's the atmosphere. So let's ask the question that's going to drive the next few slides. How is the Earth warmed? And that's the question I'll pose to you guys. It's a one-word answer or a two-word answer. And I've already given you the answer, but you can say it out loud or you can put it in the chat. It's a very simple answer. What warms, oh damn, I jumped the gun. What warms the planet? You guys learned about this when you were little. Well, you're jumping the gun, Sam.
The sun.
Yep. I told you one or two word answer. Sam, you're right, technically, which some people would say is the best kind of right, but you're jumping the gun on me here. We'll get to greenhouse gases in a minute, but it all starts 93 million miles away, it's technically called 1 AU, one astronomical unit. And that starts with our friend, the sun. The sun, as we've sort of discussed, is the backbone of everything on this planet. It warms the planet. It gives us light for photosynthesis, which feeds the entire planet. The sun is the backbone of our planet. And so it warms the planet. The sun's rays travel through the vacuum of space, heat the planet up, warming the planet. And that's, again, you learned about this when you were little, right? The sun warms the planet. So let's talk about how that works. Now, there's two facets to how the planet warms relative to because of the sun. Now, the first is actually called reflectivity. Now, I'm going to give you an example of what reflectivity looks like, and it's something you guys have all experienced, provided you've driven in a car of some sort. So I'll give you an example from my life because it happens all the time. Now, pretend you're, well, I'll just tell you, but this, so in my life, I drive a black car because I think black is the best looking of all the car colors. Just my opinion. And I have a friend that drives a white car. You know, we like to get together. We like to go to Chipotle, you know, once every month or so, you know, to hang out because he's got kids and, you know, we got jobs and all that fun stuff. So we like to go to Chipotle every now and then with one another. He drives a white car, I drive a black car. Now, in the summer, we go to Chipotle, we go there, we're usually there for like 3 hours because, you know, when you don't see your best buddy for a month, you got a lot to talk about, right? So we're there for like 3 hours sitting on those uncomfortable Chipotle chairs. And when we go out to our cars after our 3-hour hang session at Chipotle, I get in my car and my car is sweltering hot. It doesn't matter if it's the winter or the summer. If that sun is out, my car is sweltering hot. He hops into his little white Volkswagen and he's all nice and cool. It's a little bit hot, but he could sit in his car for 20 minutes and not pass out from heat exhaustion. I would sit in my car for 5 minutes and I'd pass out because it's so hot. Now, why is that the case? Well, it's actually what we call the reflectivity or the albedo of the car. So darker surfaces absorb more sunlight, right? So black surfaces, dark gray, blues, oranges, deeper reds, they absorb a lot of energy from the sun, thus warming them. Conversely, his white car reflects most of the light back away from this car, meaning it doesn't absorb a lot of light, i.e. a lot of heat. So this nice example of my friend's car and my car is hot because its albedo is actually very, very low. Its reflectivity is very, very low. His car stays cooler because his albedo is very, very high. His reflectivity is high. So that's one example. Now, the other example I'll give you is actually just something that if you own a pet, you should actually just really know. So I'm sure for those of you that have pets, you take them on walks and stuff like that. But the one thing you should know about taking any pet on a walk is that you should have to be careful at the air temperature. Now, 80 degrees might not seem very hot, but the reality is dark surfaces like asphalt and cement actually absorb a lot of sunlight. And so they actually absorb a lot of energy from the sun, making them much hotter than the air around them. So on an 80-degree day, asphalt is usually close to 115 degrees. On a 90-degree day, asphalt usually pushes about 130 degrees. Those temperatures are actually too hot for doggies' little pitty-patty feet. So albedo plays a role in how hot your dog's feet get. Conversely, it also plays a role in how hot your feet get if you decide to walk barefoot outside. But again, it all comes down to the albedo. So let's take that idea of albedo, of doggy's feet and me and my buddy's cars, and let's apply it to the earth. Different spots in the earth have different albedo. So areas that are covered in ice have very, very high albedo. It means they reflect a lot of light. So snow and ice reflects 80 to 90% of all the sunlight that hits it right back up into the atmosphere and potentially into outer space. Whereas only a small amount is actually physically absorbed. Conversely, sunlight that hits, say, a dark brown patch, so soil, or maybe mud, or potentially the water, or say green forests, those are darker surfaces. Thus, they absorb more sunlight, thus warming faster. So the Earth, when it's not covered in snow, it's much, much warmer. The Earth, when it's completely covered in snow, much, much cooler. Why? Well, there's lots of reasons for that, but one of the main driving reasons is the albedo. So darker surfaces absorb more sun, make it warmer. More whiter surfaces, lighter colors, reflect more back. This is why your mom probably told you when you're a kid to wear light clothing when you go out in the hot summer, because you'll stay cooler. So the reflectivity really does influence how much how warm the planet gets. Now, the other aspect of this that, again, it ties directly into the albedo. They're all part of the same cog, and I think it was Sam that mentioned it already. But it's the greenhouse effect, greenhouse gases. Now, what is this? You guys have heard of this term probably for years. I remember I heard it back when I was, I think, 6 years old. Really, really young. I've heard this term for decades now. Now, what does the greenhouse effect actually mean? Well, the greenhouse effect is just a really simple but really important phenomena that occurs naturally across the planet. People, like most things in our society, things get easily politicized. The greenhouse effect has got easily politicized as well, as has climate change. We'll talk about that later. But the greenhouse effect is natural. Even if humans had never existed, the greenhouse effect would work here. That's just the reality of it. So what is it? Well, it's based upon the idea of how a greenhouse works. Now, for those of you that have never been in a greenhouse, they're just, they can be variable in shapes, but, they're just a structure with thick glass. Now, this thick glass acts to let the sun's energy into the greenhouse, but helps prevent the energy from the sun escaping the greenhouse. So you can have a greenhouse in the middle of a New England winter, minus 10 degrees, and that greenhouse is a nice 70 degrees. So why is that? Well, the panes of glass are acting as essentially a barrier, like a warm blanket over that structure, trapping heat, keeping it warm. And that's the exact same thing the greenhouse effect does. But instead of a nice warm blanket, or instead of nice thick glass panes, it's simply gases found in our atmosphere. So we have a couple gases that are really, really important. So we have our friend and foe, carbon dioxide, water vapor, methane, and a few others we'll mention in a little bit. They act as like that warm blanket. So when energy from the sun hits the earth, as this example sort of shows you, some of it's directly absorbed, thus warming the area. But as you'll notice, even on these places that have low albedo, right, some of it is still reflected back up. But in the case of places where high albedo, a lot of it is reflected right back up. Now, where does that go? Well, a lot of it actually simply goes right back up into outer space. So it just leaves the planet. But the stuff that actually gets trapped by our greenhouse gases. So our greenhouse gases act as that that warm blanket. The reflective energy from the planet hits the greenhouse gases and gets sent right back down to the planet Earth, thus warming the planet. So that's our greenhouse gas. It's, again, think about it as like a warm blanket, right? Warm blankets aren't perfect, right? They let some heat out of your body, but they trap in a significant proportion of heat. And the greenhouse effect is the exact same way. So let's do a little thought exercise. I have two little thought exercises surrounding the greenhouse effect. So let's and if you looked at these slides before class, don't spoil it for other people. So tell me what you guys think. Now, let's pretend we have a planet where there is greenhouse gases, so i.e. modern Earth. What do you guys think the mean global temperature of planet Earth is right now? Could be in degrees centigrade or Fahrenheit, either way.
Maybe like 60 degrees Fahrenheit.
I did not see who said that, but you are absolutely 100% correct. It is about 60 degrees Fahrenheit. Good guess. You were pretty damn close to Will at 67 degrees. But yeah, it's actually 59 to 60 degrees Fahrenheit. That's the average global temperature. So again, I didn't see who it was, but fantastic first guess. And I hope that was just off the top of the head guess and not I looked at the slides guess. All right, so that's our current mean global temperature. Now, let's pretend we stripped away the greenhouse gases and there's no greenhouse effect on our planet. What temperature, given that greenhouse gases warm our planet, what temperature do you guys think our planet would be without any greenhouse gases? Well, it's certainly going to be less than 60 degrees, right? But how cold? How cold are we going to get? Or how warm are we going to get? Maybe it goes the other way. I don't know. Minus 20. Alex, is that minus 20 centigrade or minus 20 Fahrenheit, Alex?
I was thinking Fahrenheit, but maybe even Celsius.
Well, the Celsius one would be closer. Minus 20 Fahrenheit is a little bit too cold, but I like the way you're thinking. So it's warmer than -20. I will say that. What do you guys think? There's no wrong answers here, but we know it's somewhere between -20 and 60 degrees Fahrenheit, of course, because we're in America. We use Fahrenheit, right? What do you guys think? How cold would the planet degrees? Damn, you guys are good. Yep. So Katerina hits the nail right on the head. It would actually be 0 degrees Fahrenheit or 0 degrees centigrade, 0 degrees Fahrenheit, or about like -15 or so centigrade. So our planet without greenhouse gases would be a giant ball of ice and snow. But just by the presence of our greenhouse gases, it warms our Earth by 59 degrees Fahrenheit, or around 17-ish centigrade. Pretty remarkable, right? That's just the natural greenhouse effect. That's like no humans coming in and doing anything. That's just what the planet is doing naturally. 60 degrees. And so let's talk about those greenhouse gases. Right? Who are these guys? Who are these gases that for $0 a day, right, warm our planet by 60 degrees Fahrenheit? So these gases are rare, right? I've already mentioned a few of them. We have water vapor. That's about 95% of all greenhouse gases in the atmosphere. Carbon dioxide sits at about 3.6%. And then there's a group of other gases, which I'll make mention of in just a second, that comprise about 1.4%. So our greenhouse gases, again, they're part of that club that is less than 1%, but they exert a huge effect on our planet, right? 60 degrees warming is no joke, right? That's like the difference between living in really far up Canada and like here in New England, right? That's a huge effect. But the key here is more greenhouse gases means you have more trapped heat, which leads to a warmer planet, right? This idea shows you that. But again, think about it as like the blanket, right? The greenhouse gases are a blanket. So if you had like a sheet from your bed, that's not very insulating, right? You'll get cold, right, during the winter, or if you have the air conditioner on, right? But if you grab a nice, thick, warm blanket and you toss it over yourself, you're all nice and snuggly, right? Because that warm, thick blanket traps more heat, thus makes you warmer. And the greenhouse gases are the same way. The more greenhouse gas you have, the more heat you'll trap, the warmer our planet, not planter, is. Not planter, planet, planter. So let's do a final little thought exercise surrounding the greenhouse effect. Now, we're going to look at the two closest celestial bodies to the Earth. So we have our Mars, where the Curiosity rover is, doing its thing. Mars is a pretty cool planet. It's obviously uninhabited by, at least as far as we know, though they think there's bacterial life in the soil, which is exciting prospect. But it has a very, very thin atmosphere. It basically has no CO2 in its entire atmosphere. And then we have Earth, which atmosphere is about 3%, or sorry, 0.03% is CO2. That's where we live, right? We know the average temperature is again about 60 degrees Fahrenheit. And then we have our friend Venus, which has a really, really thick atmosphere. Like it is super thick, super dense, but its atmosphere is not like ours. It's actually 96% carbon dioxide. So another thought exercise: how warm do you think Mars is? We know Earth is about 60 degrees. And how warm do you think Venus is? So we'll start with Mars. No CO2 in its atmosphere. Very, very thin atmosphere. What is the temperature of Mars? What do you guys think? Not a single guess. Oh, sad. Okay. Well, I don't have any guesses, but it's cold, and so we'll jump ahead. No one wants to entertain me. So the average temperature across Mars is actually -50 degrees centigrade. So really, really cold. I don't know if you guys have ever been in -50 degrees centigrade, but it hurts like a lot. And I say that because I was in Montreal a couple of years ago and it was -45 degrees centigrade and it hurt quite a bit. So Minus 50 degrees is no joke cold. Then we have planet Earth at about plus 15 degrees centigrade, which again is about, that 60-degree mark. And then we have our friend Venus, and it's actually the average temperature on Venus is about 420 degrees centigrade, which for those of you that don't know how hot that is 4 times the boiling point of water. So that would be close to 800 degrees Fahrenheit. So super duper hot. Why is that the case? Well, the sun, this one is closer to the sun, and that does factor in a little bit. But what's really driving these patterns here is how much CO2, right? How much greenhouse gas do these places have? A runaway greenhouse effect makes you super duper hot. No greenhouse effect makes you super duper cold. So the greenhouse effect, it's natural, right? It's an important part of warming our planet. It makes our planet habitable. But as you can see with our friend Venus, and as you can see with our friend of Mars, not enough greenhouse effect or too much greenhouse effect, you're kind of out of you're kind of down creek without a paddle, right? You're out of luck. So let's talk about let's talk a little bit in depth about our greenhouse gases. So we'll talk about them sort of naturally, how they occur naturally. So the first one is our friend water vapor. What's water vapor? Well, it's just evaporated water, right? When water evaporates from a puddle or a pond or the ocean, it goes up as a gaseous form into the atmosphere. It hangs around for a bit, but it oftentimes gets rained down or snowed down, right? That's water vapor. Now, water vapor contributes to about 60% of the greenhouse effect we see here on the planet. But the important thing about water vapor, it is directly controlled by temperature. Now, what do I mean by that? Well, places that have very, very cold temperatures, such as the Arctic or the Antarctic, they actually have very little water vapor coming off the surface. Why? Well, they're colder, right? So when the temperature of the planet is cold, there's very little water vapor in the air. It's all condensed into snow and ice, right? But then we sort of go down in latitude to the tropics. And for those of you that have ever been to the tropics, the tropics are really, really humid. Now, why is that? Well, the tropics are warm. Thus, we have more evaporated water. Thus, we have more water vapor coming off the tropics. So while water vapor is important, it's 60% of natural warming, it is directly controlled by temperature. So it's not the other way around. Water vapor doesn't cause climate change. Water vapor is just a part of climate change. And it is, again, the warmer the planet gets, the more water vapor we're going to see in the atmosphere. So that's our friend water vapor. Then we have carbon dioxide. Now, naturally speaking, carbon dioxide comes from the decay of living material. So if I have a sandwich and I throw it in the garbage, that sandwich will disappear in a month or so. What happened to it? Well, a bunch of organisms ate it, right? Bacteria and fungus, they ate it. They chewed it up and then they respired it out, right? You guys know you breathe in oxygen and you expel CO2. That's what we're going at, right? When dead material breaks down, CO2 is the byproduct. So that's our friend CO2. Then we have methane. Methane actually has only one single source naturally, and that's actually from soil microorganisms. Just part of their metabolism, they produce methane. They're called methanogens. They're pretty cool, but they are just the only group of organisms that we know of that naturally produce methane. Then we have nitrous oxide, which actually has 2 natural sources. I put just one of the sources because the most important source of nitrous oxide as a greenhouse gas is actually microscopic organisms, mostly in the ocean. The ocean contributes about 75% of all nitrous oxide to the atmosphere. But soil microorganisms also gives us some of this greenhouse gas as well. Now, the other small component of nitrous oxide, which I think is the coolest component, even though I study the microbes that produce nitrous oxide, ironically, is actually nitrous oxide can be produced via lightning. So when lightning sparks, it takes all that nitrogen, some of that nitrogen in our atmosphere and converts it to nitrous oxide. So just as a note, natural source is primarily from microbes. We can also produce nitrous oxide through the badass process of lightning, which is obviously pretty cool. And then the other major greenhouse gas is actually a synthetic gas. They're chlorinated and fluorinated gases. They only come from humans. There's no natural gases there. So let's look at a table. This is from the IPCC. We'll talk about the IPCC later in class today. But this is just their awesome little table that I like to steal every time I do this, where we have all these different greenhouse gases, their chemical formulas, and then we have their global warming potential over a 100-year period. Now, they're all standardized, as you'll notice, to carbon dioxide. So carbon dioxide, one single molecule of it does X amount of warming to the planet. A very, very small amount when you think about one molecule of carbon dioxide. But All the rest of them are normalized to how much carbon dioxide warms. So you'll notice that methane warms the planet 25 times more over a 100-year period than carbon dioxide. Nitrous oxide, 265 times. And these gases, these synthetic ones, whether it's these CFCs or HFCs or these things that are used in electrical components, have potentials thousands. In the case of sulfur hexafluoride, 23,000 times the potential warming of CO2. So not all greenhouse gases are created equally. They're just not. But the other thing you'll notice is that they have unequal lifespans in the atmosphere. Carbon dioxide hangs around for about 100 years. Methane, only about 12. Nitrous oxide, 120. And then you'll see some of these last for hundreds of years, right? So these synthetic gases down here last 100+ years. So if we wiped out the wild thing to think about is that even if humans just stopped polluting, if these gases would affect our planet for hundreds and sometimes thousands of years into the future, which is kind of a wild thing to think about, right? That something we produce today will still be in the atmosphere in the 2100s, right? Which is kind of a crazy thing to think about. And in the case of sulfur hexafluoride, it'll be there in the year 5000, right? Which is really far off, but kind of a cool thing to think about. So those are our greenhouse gases. We'll talk about the anthropogenic, i.e. the human sources of all these gases in a few slides, but let's look at the natural variability of Earth's climate, because the important thing about the Earth's climate is it's not static. It changes over time. But I'm going to show you that the time frames by which the climate of the planet changes are just not on the scale that we're seeing today. So let's look at an 800,000-year look at the Earth's climate. Now, how do we do this? Well, as you guys probably see from these pictures, we look at ice cores. Now, how does ice form? Right? When you think about a glacier, when you think about like Russia, or you think about the Antarctic or the Arctic or Greenland, how does the ice form there? Well, it all starts with the atmosphere, right? Water vapor gets in the atmosphere. It falls down as snow. As snow gets compacted on top of one another, it starts to melt, right? Snow is a great insulator. That's why Eskimos make igloos, right? Snow is a fantastic insulator. So as snow gets packed on top of one another, it starts to melt the snow in lower layers. So, but once that snow melts, it's liquid water, but it's still the Arctic. So it will refreeze, thus forming ice. So that's how ice forms, but why do we care about it in the context of a core? Well, the reality is it's actually just a really nice record. The deeper down you go in an ice core, the older the ice gets. And so just to sort of put that in perspective, it's kind of like a tree ring. So for those of you guys that have ever cut down a tree or seen a tree chopped down, you guys know trees have rings. And the farther out the ring is, ironically, the older the tree actually is, right? So the bigger the tree, the more rings it has, the older the tree is. But the interesting thing about a tree is that the rings in the center are younger than the rings at the edge of the tree. In fact, just as a note, the rings at the end of the tree are basically just dead tissue, just as a note. But an ice core is the same way. The deeper you go, the older the ice gets. So it provides a really nice record of the atmosphere. Now, why does it provide a record of the atmosphere? Well, when ice freezes, and you guys have seen this when you got ice from the freezer, gas gets trapped in ice. And so an ice core is actually a perfect geologic record of the Earth's atmosphere. Because as I mentioned, the Earth's atmosphere is pretty dang consistent across the entire planet. So the ice in the Arctic reflects the atmosphere, the gas trapped in the Arctic ice is reflective of the gas in the atmosphere at that given moment in time. So it's a really cool sort of phenomenon. We can look at ice cores and understand what the atmosphere of the planet used to look like, which is, I think, is wild. And actually, I gave this same talk to my other section of this class on Friday, and I had an electrician in the room working on putting a new fan really high up in my house, and he after the fact he was like, I never knew that about ice cores. That's really cool. He's like, I'm gonna go home and look up that because again, I don't know, I just think it's just a really cool phenomenon. So ice cores give us an ancient look at our atmosphere. Deeper you go, the older the ice. Now, the ice traps gas. Now we can look at any number of gases trapped in that ice, but we're going to look at CO2. And the cool thing about of ice cores in the atmosphere as a general, we can actually look at oxygen and what are called isotopes. You don't need to worry yourself at what that means, but different types, different ratios of oxygen isotopes indicate different temperatures. Just to let you know. So these ice cores let us look at the atmosphere, look at its composition, and estimate the global temperature, or at least the temperature locally, I should say. So those are the two important things. Again, I love this stuff. It looks really cool. But let's look at the data. Let's look at what we see. So we have two graphs here. We have carbon dioxide in the blue, Antarctic temperature in red at the bottom. You see we start at 800,000 years on the left, going all the way to about modern times on the right. We have carbon dioxide in parts per million, and Antarctic temperature. In this case, it could also be the Arctic, doesn't really matter, and temperatures in degrees centigrade. Now, just as a reminder, parts per million simply refers to if I had, say, 1 million jelly beans, and I had one of them was red, and 999,000, blah, 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 were green, I'd have 1 parts per million red jelly bean. That's what parts per million means. And so if I have 300, for instance, means of my million things, 300 are, say, red, and the rest are blue or green. So just as a refresher. So what do we have? What patterns do you guys see? There's a couple things I'd like you to sort of pick out. But what do you guys see? Have you ever seen this before?
The trends for carbon dioxide and Antarctic temperature seem to follow the same shape of the lines.
Yep, that's the most important thing to take away from this is that, yeah, they track pretty damn close. So you'll notice that when carbon dioxide goes up, temperature is there with it. And when they go down, they're together, right? Even like weird little blips like this, they track one another. Now, the question is, what's driving which? Well, temperature doesn't drive carbon dioxide. Carbon dioxide drives temperature, right? That's the greenhouse effect. So when carbon dioxide goes up, temperature goes along with it. And we see that not just 800,000 years ago or 600 or 400, we see that now, right? And it's a consistent trend. Now, the cool thing you can do with this data, if you plot them, so if you plot CO2 on the x-axis and temperature on the y-axis, you actually get this really fantastic, almost perfectly linear trend, which is kind of wild. And it's wild simply because it's an 800,000 year record, right? So as CO2 change in the absence of humans, remember the Anthropocene is defined by this little tiny slice right here. Right, just down here, we're down at this back end, right? We're on the clock, we're the fractions of second, right at the end. The carbon dioxide influences temperature. Now, what else do you notice? Is there anything else that you should take away? I guess I'm kind of giving it away by asking you the question, but anything else? Well, the other thing that I think is remarkable is how janky these lines are, right? I mean, look at this thing. I mean, this is long time periods, don't get me wrong, but look at this line. Look how much this line jumps around from, I mean, these are thousands of year time periods, but it's not consistent. And it almost goes in, you kind of will notice in like little wave functions here too, right? It kind of comes up repeatedly. And so 2 key takeaways. As CO2 increases, as does our temperature in the absence of humans. That's the greenhouse effect. But there is significant variability in not just CO2, but also the temperature of our planet. So it's a pretty remarkable sort of set of graphs, right? 800,000 year look. And those are the 2 key takeaways. So what else can we learn from those ice cores? Well, the first is actually one of the things you may or may not have noticed is that CO2 never eclipsed in this time period more than 300 parts per million. You guys probably have heard CO2 is at about 420 parts per million right now. So in a million year period, basically, we haven't seen CO2 eclipse 300 parts per million. So that's kind of a cool thing. Now, the other thing we noticed from these cores is actually methane and nitrous oxide are also higher, but we'll get to those later today. And it's the other sort of thing is actually what it looks like. So when you have a few minutes, there's this really fantastic YouTube video. I think it's from NOAA, if I'm not mistaken. Take a peek at this YouTube video to visualize this record over time. It's a really remarkable video because it puts this, the patterns that you see here into some pretty stark contrast of what this actually looks like, and in particular, what this end of this graph really looks like. So definitely take a peek at this YouTube video. It's a pretty cool thing. Now, as I mentioned, you'll notice that there's natural variability in the climate. So let's talk about that. Let's talk about what causes Earth's climate to change in the absence of humans. And so we're gonna talk about changes in the sun's intensity in about 2 slides. So don't forget about changes in the sun's intensities. But the first 3 that I wanna talk about are actually what we call collectively Milankovitch cycles. Now, this this figure down here really says all that needs to be said, because they're actually relatively easy to sort of grasp. Now, as you guys may or may not know, depending on how much you like space, the Earth orbits in essentially an egg-like shape, right? It has an ovular shape. Now, that's the orbit we're in right now. Every 100,000 years or so, and I'm not an expert on this. I don't know why it is off the top of my head. There's an astronomy and physics answer to this question. So if you want to know the answer, you'll have to Google it because it's beyond my my wheelhouse. Just as a note, the Earth switches from this egg-shaped orbit to this perfectly circular orbit. Now, you might ask yourself, why does that matter? Well, this is closer than this, right? We get pretty dang close over here and over here, but the reality is, if we're closer to the sun, like say Mercury, we're not getting that close, obviously, but the closer you are to the sun, the warmer you are, right? Mercury is a blistering hot 900 degrees centigrade. Neptune and Pluto, way out at the edge of the solar system, are essentially at the below the freezing point of water. So the closer you are to the sun, the warmer you are. And so in this case, if we switch to a circular orbit, we would be warmer as a planet. And that happens about every 100,000 years. And you can sort of see it, right? We sort of switch down to be colder, right? And the temperature gets a little bit colder. So these cycles occur, again, every 100,000 years. Then we have a change in the Earth's obliquity. You guys probably know the Earth is not perfectly straight up in space, right? It's not like Uranus or Neptune, which are perfectly vertical. The Earth actually exists at a 23.5 degree tilt. Just the axis of the Earth is just slightly tilted. And it's tilted right in the middle of the extremes. And so every 40,000 years, the Earth cycles between being 24.5 degrees angled toward the sun and 22.5 degrees angled towards the sun as well. We're right smack dab in the middle right now. And so that changes. Now, why does that matter? Well, remember, how warm an area gets is all relative to how much solar radiation hits the Earth, right? When we talked about in our class about the atmosphere and stuff like that, and weather and stuff like that, the places that get more direct sunlight are simply warmer, right? The equator is way warmer than Massachusetts because it gets more direct sunlight. So if you change the angle, you change which places get more direct sunlight, which thus can change the climate in those regions. But we're right smack dab in the middle right now. It takes a very, very long time. We're not seeing any meaningful changes in our current lifetimes to changes in the obliquity of our planet. And then the final is actually the precession. It's just simply the wobble of the Earth. The Earth doesn't perfectly it's kind of a weird thing to think about, but the Earth kind of wobbles as it spins on a daily basis. And as it sort of wobbles, it wobbles, changing what we would typically consider our North Star. So right now, our North Star is the perfect north for us in terms of a compass. But every 26,000 years or so, the wobble changes to being significantly slimmer, giving us a North Star of Vega as opposed to our standard variety North Star. But again, changes in the wobble, very much like the changes in the obliquity or the eccentricity, change how much solar radiation we get, thus impacting global climate. But I will say about these 3 things, they're simply out of step of what we're seeing. We're in a cycle of an egg-shaped orbit. We're right smack dab in the middle. We're not at one of the extremes of this, and we're in a really wide wobble right now. So while these things are normal, they actually don't affect us right now. So the modern type of climate change we're seeing is out of step with our friend, the Milankovitch cycles. So just as a note, but in the past, again, they do influence Earth's climate. That is 100% sure. But right now, not really playing a big role. Now, another part of our thing, of our Earth's climate, which you guys may have experienced in your lifetime, is actually our friend El Nino. I forgot to put the little squiggly line over the end, but El Nino. Well, I did it here, actually. And the opposite of El Nino was this La Nina. So let's actually just ignore the text. Let's actually just look at what El Nino and La Nina is. So La Nina is basically what I would call, and scientists basically call, business as usual. This is what naturally happens in this part of the world. Now, remember, the Pacific Ocean is colossal. Remember, it is huge. The Pacific Ocean alone covers about 30% of the planet. So it is huge. So anything that happens in the Pacific Ocean, climate-wise, is kind of a big deal globally. But what happens normally is there's this westerly wind that pushes warm water and warm air, for that matter, but we really mostly care about warm water off the coast of Central and South America. So, where you have all the parts of like Panama and Mexico and, all the other countries in Central and South America. It takes all that warm air, warm water, pushes it off the coast towards our friends in Australia and the Indo-Pacific Islands, and obviously past Hawaii as well, causing all that warm water to pool in this area of the world, which is already pretty warm. So that's La Nina. Now, what does that do? Why is that important? Well, as you push warm water away from this part, some water has to replace it. So where does that water come from? Well, it just comes from deep down. So during La Nina, warm water goes this way, cold water comes up from the bottom. It's called upwelling. And so it makes this area of the country, of our country and Mexico and all the other countries, significantly cooler than they should be, given where they are in the world. Remember, the equator is about here. So La Nina is awesome. It makes these places cooler. Gives it more rain and all this stuff. La Nina is awesome. The other thing it does is as you bring in cold water from down below, that cold water actually brings a bunch of nutrients with it. And so all those extra nutrients actually stimulate plankton, so lots of photosynthetic organisms, which actually then in turn stimulates sardines and the fishing industry as a whole. So La Nina, much cooler climate here and globally for that matter, and stimulates the fishing industry in this area of the world. So that's La Nina. La Nina is awesome. El Nino is, for lack of a better word, just a big jerk. So during El Nino, those westerly winds actually shut down. And what ends up happening is warm water pools here and pools over large sections of the Pacific Ocean. Makes Australia a little bit cooler and Indonesia and all those islands, but it makes the Pacific Ocean as a whole significantly hotter. And you can imagine that does two things. Given how big the Pacific Ocean is, it makes the planet warmer. That's what it does. So during El Nino years, the Earth is about a degree warmer, which again, doesn't sound like a lot, but actually is when you think about it at a global level. And the other thing it does is shuts down all the nice cool waters coming up from below. So it actually dramatically reduces the fishing industry in this area of the world. So it has both a weather effect and a climate effect, but also an economic effect as well. So El Nino and La Nina, they're perfectly natural. They cycle every decade or so. And they're pretty dang important to the overall climate of not just the Pacific Rim here, but also for the planet as a whole, given how big the Pacific Ocean is. So that's our second group. So we have the Milankovitch cycles. We have our friends El Nino and La Nina. The next one and the second to last one is actually going to be what we call volcanism. I don't mean volcanism like Star Trek. I mean volcanism as in volcanoes. Now, volcanoes are pretty cool. You guys probably know volcanoes are just parts of the earth where the magma from deep down erupts, and it spills out and it spills a bunch of gas out. Now, sounds cool, right? Pretty destructive for the places that get hit with lava and all that and the gas and stuff like that. But actually, when any volcano erupts, it puts a couple gases into the atmosphere. Now, we're going to ignore most of the stuff on this graph because it's really just not really what we care. But actually, the two gases we're going to focus on are actually our friend CO2 here and this gas here, which we call sulfur dioxide, SO2. Now, it puts a lot of CO2 in the atmosphere, which you would imagine would warm the planet, and you would be right for an extent. When large volcanoes erupt, the CO2 does rise the temperature a little bit. However, it is actually dramatically counteracted by sulfur dioxide. Now, sulfur dioxide is actually basically like a like a reverse greenhouse gas, it actually acts to increase the albedo of the planet. So you can sort of see that in this figure here. When there's a lot of sulfur dioxide in the atmosphere, it actually reflects a lot of solar radiation right back out into space, actually cooling the planet. So as you can see with this graph here from the also fun scientists at UC Berkeley, where you have the average land temperature here on the X, on the Y, and time since 1750 on the X. Every time there's a major volcano eruption, Krakatoa, El Chichon, or Laki, or any of the other ones that you see here, you see a precipitous drop in the Earth's global temperature, sometimes by close to 1.5 degrees. So sulfur dioxide is great. It cools the planet. It completely offsets any CO2 that the volcano puts in the atmosphere. But you'll notice that the temperature bounces back within 5 years or so. And so volcanoes act to change and cool the planet on very short-term scales. However, they simply only are short-term solutions. Sulfur dioxide only hangs around the atmosphere for a couple of years before it goes away. So that's our volcanoes. They're pretty cool. Now, the final aspect of Earth's climate is actually the variability in solar radiation. You guys might have heard of sunspots at some point in your life, or maybe you've never heard of them. But a sunspot, when you look at a picture of the sun, is simply little black dots, sometimes large black dots actually, that appear on the surface of the sun. Now, there's some fancy, like physics about what's happening with the sunspot that we won't get into. But you should know that the more sunspots that the sun has, more solar radiation makes it to the planet. Thus, the planet gets slightly warmer. So the cool thing about sunspot cycles is they occur on about 11-year time periods. And you can see that here at the bottom in this orangey color. Every 11 years, the sunspots peak. 11 years later, they're at the low. They peak every 11 years, and they're down 11 years, and so on and so forth. And that's just the pattern we see. Now, you'll notice that they've gotten slightly more abundant in modern times. The sun is changing. The sun is not a static entity. It changes over time pretty dramatically. But you'll notice two things. The first is that we have our friend here, CO2. It's going up and up and up. And then we have our temperature. You'll notice that temperature really doesn't meaningfully track sunspot cycles, right? So when there's a massive peak here, there's not a corresponding massive peak in the temperature anomaly we see on the planet. So the key takeaway here is that, yeah, sunspots matter a little bit, but they actually don't affect the Earth's climate by more than a fraction of a degree. And the increase in temperature we're seeing is simply out of step with sunspot cycles. Because you would imagine if we track sunspot cycles perfectly, and that was what was causing climate change, at least modern climate change, every time there was a huge peak, the Earth's temperature would go crazy. But it's simply not the case. So all these factors, sunspots, volcanism, El Nino, our Milankovitch cycles, they all affect the Earth's climate, but they simply are out of step with the rate of the change in the Earth's temperature that we're seeing right now. So this brings us to our graph that we started off with, right? The first piece of data we looked at together, modern climate change, this trend. So the question we can ask is, what's causing this? And the short answer is humans, right? That's it, right? It's humans. So how do we know climate is changing faster than normal? Because that's the really important part, is that it's happening, not that just that it's happening, right? Because the 800,000-year look should convince you that the Earth's climate changes, but the key here is that it changes on such long time periods that what we're seeing now is so rapid. It's something the Earth has actually never seen. This change of 400 to 410 parts per million, right? A 10 parts per million increase, that takes usually tens of thousands of years to happen naturally. But we're doing it in 100, in this case, just 5 years. So the important thing to take away from this graph is actually the rate. The rate at which climate change is happening has never, and I mean ever, been seen on this planet, ever. That's the concerning part. Not that climate is changing. I mean, the climate change obviously is really bad, but how fast it is changing tells us that it simply is not a natural thing any longer. We're out of step with what nature is doing. So just to put you into perspective, this is some data from NOAA. We can see that we have, ends in about just before 2020, where CO2 is at about 412 parts per million. As of August 4th, it's at 415.67 parts per million. And if you want to see what that looks like, definitely take a peek at this video. It's from Vox. They make cool videos as well as cool graphics. So lots and lots of CO2. It's increasing faster than it's ever before. Now, the final thing I'll make mention is actually, I've sort of given it a name here. It's called the Keeling curve. It's this red line. Anybody know what the Keeling curve tells us? It goes up and then down and up and down, but it does this every year, up and down and up and down. This is in Hawaii. It's at the Mauna Loa Observatory. So it's in the Northern Hemisphere. It goes up and then comes down, up and down. Anybody know what that up and down might be due to? If you watch the video, it'll explain it too, but I wanted to make mention of it. Well, it's actually just seasonal changes. So when CO2 increases, it's actually the winter in the Northern Hemisphere. When CO2 goes down, it's actually the summer in the Northern Hemisphere. You got to remember, about 70% of all the land is in the Northern Hemisphere. So when the Northern Hemisphere is in winter, plants are not doing their things. Dead stuff starts to decompose really fast, so CO2 goes up. During the summer, when plants are going crazy, CO2 comes down. You'll notice it comes down by, 7 parts per million between summer and winter. So I just wanted to point that out. This Keeling curve again is the Earth breathing. It's kind of a cool thing. So that's where we're at. So let's talk about how humans come into play. Where is it, right? We're not affecting the sun. What we affect is the greenhouse gases, right? So we know the normal greenhouse gas in the atmosphere, mostly water vapor, mostly CO2, and there's some other stuff that we've mentioned. But humans, we put a lot of greenhouse gases in there, and we put mostly 3 types of gases into the atmosphere. So the big player, as you can see from this mighty pie chart, if you're eating pizza and this is how you cut your pizza, you'd have a monstrous piece of pizza, right? Most of it's carbon dioxide, 85, 84%. We have methane, 9%, nitrous oxide at about 5%, and then fluorinated and other type of gases comprise the remaining 2%. So CO2 is the most important. It's not the strongest greenhouse gas as we discussed, but it is the single most important gas that we put in the atmosphere. Now, what puts it in the atmosphere? Well, it's actually pretty simple. It's just what we do. Right? The result of the Industrial Revolution is switching from cows and donkeys and stuff like that, plowing our fields and bringing us from Philadelphia to Boston, to I hop on a train, I hop in a car. And those cars, those trains run on a specific type of fuel, which we simply call fossil fuels. You guys have heard that term. Why are they called fossil fuels? Well, fossil fuels, coal, oil, natural gas, they all come from deep down in the planet, and they are the result of ancient creatures that have died, and the extreme pressures of the planet have converted them into coal. So coal is actually the result of ferns and other trees being heated and compressed deep down in the earth. And gas is actually the result of algae that have died and been compressed, forming the petroleum that we know and unfortunately have to love at this point in time. So they're called fossil fuels because they're a result of long dead creatures. And now these fuels, as you guys probably have heard, they're non-renewable. Now, what does that mean? Well, it simply means that if we got rid of all the fossil fuels on the planet right now, it would take millions of years, right? Way longer than a human lifespan to regenerate all those fossil fuels. So they are not renewable. Once they're gone, which they're not that far off from being, they're gone. So and I'll just put that in contrast to, like, say, wind energy, which, say, if it's a windy day one day, that doesn't mean the wind's gone, right? It means the wind will be back tomorrow or the day after, right? So those are renewable because they come back on a human time scale. So let's look at this. So we have methane here at the top in blue. You'll see methane is pretty static at about 700 parts per billion, and then shoots up around the Industrial Revolution, 1800s. We have nitrous oxide hanging around at 260, 280 parts per billion, shoots up at about the same time methane does. CO2 hanging around 280 parts per million, shoots up again about the time of the Industrial Revolution. And then the final figure, we're going to ignore the red line up here. Don't concern yourself with the red line. The green line goes up and up, is kind of increasing. Industrial Revolution, bam. So our gases in the atmosphere are becoming much more abundant because of the rapid rise in human population. And as humans grow in population size, our thirst and desire for fossil fuels to power our homes, our vehicles, our factories increases with it. So this J curve we saw with human population reflects a J curve in all 3 of the most important greenhouse gases. So let's look at this over time in a different way. These are some figures I stole from Vox, VOX. If you guys don't read Vox, I like Vox quite a bit. they make some beautiful graphics. So I like to steal their graphics whenever I have a chance. And this is one of the ones they've seen from the Global Carbon Project. So it's a quality source. It's not crap or anything like that, just because it's from Vox. But let's look at CO2 emissions in billions of tons of CO2. You'll notice that there's unequal contribution, right? It was originally just Europe and the United States, but modern times, China is by far the largest greenhouse gas emitter, but not too off of the United States and Europe. But you'll notice that other countries are expanding, right? Africa, seafaring countries, and other Asian countries are also coming up as well, as is the large group of folks in India. So CO2, again, following that nice little J curve that we see, but it's unequal contribution. Now, the stark difference between this part here, or I'm sorry, green and yellow, or blue and yellow, is actually the per capita emissions. So you'll notice that early on in the Industrial Revolution, we were emitting equal amounts of emissions per capita with Europe. But by the time the 1900s rolled around, we started emitting way more per capita than Europe. And you'll see even in modern times, we emit, about 3 times more per person than Europe or China or any other country on the planet. In the case of countries in Africa, it's 15 times, right? So the United States, while we are only 300 million people, 350 million people or so, we emit more per person than anywhere else on the planet. And then we can look at the total global emissions, right? Let's just break this down as a figure, right? You'll notice that the United States has contributed about 457 billion, about equal to what we've seen from the entire continent of Asia, slightly less than Europe and Russia, and Eastern European nations combined at 515 billion tons. And then you see the other countries here, right? Africa, a very small chunk, as is South America, and also a relatively small chunk in Oceanic, the Pacific Islands, stuff like that, with Australia leading the way. So not every continent, not every country contributes equally. Some contribute a crap ton per person. Some just contribute a crap ton just because of sheer population numbers. But who puts the CO2 in the atmosphere is not equal. Keep this figure in the back of your mind about these 3 blocks here: China, US, and EU, the 3 big, and Russia, the 4 biggest emitters. Just keep those in the back of your mind when we start to talk about the ethical issues surrounding climate change, because China has emitted more than the entire continent of Africa and South America combined. And the places that are going to be hit strongest by climate change are actually these small blocks down here. So keep that idea in the back of your mind. So where do we get our greenhouse gases from? Well, it's us, obviously, right? That's what we're talking about today. But the long answer is actually it's pretty variable, right? So the most common sources of greenhouse gases are electricity and heat at about 30%, transportation at about 16%, manufacturing at 12%, agriculture at 11%. So those 4 pieces, which touch every part of your life, make up about 2/3 of all human greenhouse gas emissions. And there's other sort of aspects to that as well, right? We have building, we have, fugitive emissions, which we won't talk about, but they're kind of an interesting thing. Land use change, right, at 6%, right? We talked about that one in biodiversity law. So lots of things contribute, but the big 4 are heat, electricity, transportation, manufacturing, and agriculture. So let's talk about CO2 first, because it's the bad boy of this. So where does most of our CO2 come from? Well, in terms of a strict source wise, remember, it's all fossil fuels, but it's the combustion of these fossil fuels, right? We combust these fossil fuels, they produce steam, which powers engines, right? That's how the combustion engine basically works. But coal has led the way for a very, very long time, and it's still a significant contribution of CO2 to the atmosphere, even in modern times. Oil is making a pretty big leap, as is gas, i.e. natural gas. So these 3 fossil fuels, gas, oil, and coal, give us a substantial fraction of our CO2 emissions. But cement also, as a building material, also releases some CO2. Now, cement is kind of cool. It's a remarkable chemical formula. It's been around for a really long time. It's been refined over time, but cement is really cool. It's really cool building material. If you've never sort of looked up cement, I recommend that you do. But so there's a cool thing. Now, a lot of cement production actually ties back into these clinkers, which look like this. If any of you are Star Wars fans, and like I am, for instance, you see clinker, and every time you think of clanker, which is what they call these little robots from Star Wars, or at least some people call them clankers. That's what I always think about. So I don't know. I thought if you're nerdy like me, you find that funny. So, but clinkers are pretty cool. Now, clinkers actually do a really cool thing is they actually participate in a chemical reaction, because cement, unlike a lot of building materials, is actually just a chemical reaction. You mix clinkers with sand and rock and a few other things, and you add water, and it drives a chemical reaction, causing cement to harden. So the cool thing about that idea is that as cement hardens, it actually gets warmer. And as it gets warmer, the chemical reaction goes faster and faster, and actually produces a crap ton of CO2, which is kind of a cool thing when you sort of think about like how cement is, right? It just looks like rock, but it's really this really cool chemical reaction that takes, dusty, dry cement and makes it into the sidewalk that you walk on. Now, the production of clinker, as well as the emissions from clinkers, is about 90% of the emissions of CO2. Only 10% actually are to these things, so transport, grinding, and cooling and stuff like that. So most of it simply comes from the chemical reaction that produces hard cement, which is kind of a weird thing to think about. You would imagine like transportation or grinding or industrial things would drive cement's carbon footprint up, but it's actually just the clinkers that do it. And so if you think about a large industrial project, like say the Hoover Dam, which has got billions of tons of cement, you can imagine billions of tons of cement emit a lot of CO2, and you'd be absolutely right. So as you can sort of see for this, while cement is not as big a CO2 emitter as gas or oil or coal, it does comprise a decent chunk, right? More than you would imagine, given as it's a building material. But remember, it's also one of the most common building materials on the planet. Now, CO2 is also hot, hot, hot. So for those of you that are fans of The Office, you know the scene from when Michael comes back from Sandals with, or is it Sandals? I forget. Is it? I feel like it's when he comes back from Sandals with Jan. Maybe it's another one when he goes someplace. I don't know. But he got these little drums, and he's always going hot, hot, hot. He's playing the song because that's all he knows how to play. Is it Jamaica? I don't know. I forget. I can never remember when it's class time. But CO2 is hot, hot, hot. Now, why is that the case? Well, as the Earth burns, as forests burn, as grasslands burn, we release a lot of CO2. Now, man-made fires account for about 96% of all fires we see on the planet. And man-made is like on accident or on purpose. So man, either purposely or accidentally, burns a lot of the planet. And most fires you see are not natural. So like the huge ones in California right now, or the huge one in Australia last year, was not natural. It was a man-made fire, either on accident or on purpose. So now, why is CO2 hot, hot, hot? Well, just to put this in perspective, those 2020 fires in California, which are just one of the many fires, large fires California's had over the past decade, actually burned through about 3.4 million acres of land. And those fires actually generated more than 91 million metric tons of carbon dioxide, which is actually, when you do the math, is about 25% more than California's annual emissions from fossil fuels, which is kind of crazy to think about, right? California's got about 40 million people. So it's got about 12% or 12 to 15% of the population in the United States. So all those millions of people produce less carbon dioxide than just one single large fire in California. So more fires means more CO2 in the atmosphere. Now, this leads us to our friend methane. Now, methane is, as I mentioned, it's naturally produced by microscopic organisms, but the big source of methane that's driven by humans is actually cows. And it's actually not cow farts, as this cow is doing in this oh so funny comic. It's actually cow burps. So cows are ruminant animals. They have multiple stomachs. I'm sure you guys have probably heard that. They ingest grass, and they rely on their microorganisms in their stomach to break down that grass. However, as they do that, they produce a ton of methane, those microorganisms in their stomach. And the cows, because it's gas, they burp it out. But when that gas gets burped out, it goes to the atmosphere, thus contributing to climate change. So our billions of cows on this planet are a significant fraction of our climate budget. Cows alone count for about 6% of all greenhouse gas emissions on the planet. So cows are no joke in terms of emissions of methane. So don't let anyone ever tell you cows are innocent, because they burp in a lot, and they produce a lot of methane. Now, what are other sources that man makes? Well, actually, one of them is actually just pipeline leaks. So natural gas, which is just methane. So some of you, like me, for instance, I heat my house with natural gas. That's just methane. And so if I'm heating my house with that, there's always leaks in pipelines and stuff like that. So our uses of natural gas help contribute to the amount of natural gas in the atmosphere. The way we grow rice right now, as well as the way we actually grow cranberries, for that matter, it's called wet rice paddies, or bogs for cranberries. It actually produces a decent chunk of methane. Coal mines, as we dig up coal, coal is actually as coal ages, it produces more and more methane, which can get out as we mine coal. And then actually one of the biggest sources of methane outside of our cow here, who's needs to just burp, is actually landfills. So let's talk about landfills. Why do we care about landfills? Well, you guys probably know you throw away a crap ton of trash on a weekly and yearly basis. And a lot of your waste is actually in food. And so what happens to all that food when it makes it to a landfill? Well, as we'll discuss, they cover landfills, trash basically, in dirt and stuff like that, which causes them to basically just be contained, which is good. But one of the things that happens is as that food hangs around in a landfill, the microbes in that food and in the landfill break down that food, producing lots of CO2 and lots of methane. And so actually, if you added up all the methane and CO2 produced on the planet from all the food wasted every year, this is in 2011, but the trend still applies. You'll notice that it would be the third largest country in terms of greenhouse gas emissions. So global food waste produced more greenhouse gas than the state of Russia, or a heavily urban area like Japan, or even a super populous region like India. So food waste is no joke in terms of greenhouse gas budgets. Third largest emitter, which always blows my mind. I see this figure year after year after year. It blows my mind how big of a contributor global food waste is to our greenhouse gas budget. Now, the sort of final thing I'll make mention about food waste, most of the food waste actually comes from two places. Your house. People throw away like pounds and pounds of food every year. It's ridiculous how much food people throw away globally, not just here in the United States, but globally. But also from like retailers, right? Like I go get a burrito at Chipotle. There's a crap ton of food waste associated with retailers. So our food choices, both at home and when we go to say Chipotle or Applebee's or wherever, influences how much food waste we produce. You'll notice that very little is actually in food manufacturing. So when you buy a can of, like, say you buy a package of Oreos, very little food waste, unsurprisingly, I think, is generated in the industrial sense, because, if manufacturers can make a buck and save money by not wasting something, they'll do it. So the manufacturing region is pretty good about not wasting food. The other one that's actually not as big as you would imagine is actually farm waste. Farms waste very little, especially relative to what the farmer wastes in his own household. So food is no joke. It really isn't. Your food choices, as we'll discuss, as you sort of probably pulled together from this, really matter, but as does what food you throw away. So now this brings us to my favorite of all the gases, and it's by far the worst gas of the trio of the big three, which is actually nitrous oxide. Now it's got two main sources. Now the first one is actually about 10 to 12% of the total nitrous oxide produced globally, according to the EPA. It comes from the combustion of fossil fuels. So as we burn fossil fuels in factories, in our cars, the reaction actually takes some of the nitrogen in our atmosphere, very much like lightning does, and converts it to nitrous oxide. So about 10 to 12% of our nitrous oxide we produce annually comes from driving cars and burning fossil fuels. The remaining 90% comes principally from our farms. In particular, farms that have very poor soil management. So you notice from this graph from the EPA, of the remaining 90%, of that 90%, 78% of nitrous oxide emissions simply come from how a farmer manages his soils. In particular, farmers that use a lot of fertilizer, that's the most important reason, produce a lot of nitrous oxide. The more fertilizer you put on your field, the more nitrous oxide you'll get out the back end. That's just the perfect linear correlation. So organic farming is technically better than traditional farming for the production of nitrous oxide. However, I'll just make mention of one thing because people ask me this question. Organic farming, because it produces way less food than traditional farming, actually produces more greenhouse gases than traditional farming does, which is kind of a weird thing to think about. But because you need more land for organic farming, all natural farming or whatever you want to call it, it's because you need so much more land to grow the same amount of food as you would do with normal farming. You simply produce more greenhouse gases, which is kind of an unfortunate thing, right? But that's just the sort of the way it is. So how we manage our fields is bad. We do it really poorly globally, and we'll talk about that in the food lecture. But you'll notice that there's lots of other things, like how we transport things, how we manage poo-poos, chemicals, and combustion and other stuff like that. So, but the most important thing is how much fertilizer you add. And in the United States, we add a crap ton of fertilizer. So we produce a crap ton of nitrous oxide. Now, the cool thing about nitrous oxide is that not every crop is equal. So we have our friend cotton here, counts for about 18% of all nitrous oxide emissions, according to the EPA. Almonds are second at about 16%, wheat, tomatoes, and then so on and so forth. So not all crops produce nitrous oxide equally, which is kind of a cool thing. So you sort of thinking about the, say like, the effects of, your milk choice, right? Whether you use, almond milk, dairy milk, or potentially you use something like, I'm pretty sure there's pistachio milk out there, but that sounds gross. Like something, say like wheat milk, or no, I'm sorry, oat milk, right? The amount of nitrous oxide produced based on those different milks is going to be different. So again, the way we manage our soils is a big deal, but also what we grow in that soil is a big deal. Now, the final thing that makes nitrous oxide a big jerk is actually what it does to ozone. So nitrous oxide actually reacts with ozone and it destroys ozone, very much like those CFCs that I mentioned before. So nitrous oxide is a double whammy. It's a very potent greenhouse gas, but it also depletes our ozone layer, which sucks, right? So our nitrous oxide production is not good for the atmosphere in a number of reasons. And then the final thing nitrous oxide does, again, making it a big jerk, is it actually reacts with the atmospheric gases, produces this little gas here, HNO3. I'm sorry, this little molecule here called HNO3, which is nitric acid. Nitric acid is a relatively weak acid, but the more nitrous oxide you produce, the more acid rain you see. So nitrous oxide is a big jerk, for lack of a better word, because again, it's a triple threat. Acid rain kills our ozone layer and causes really potent climate change. And just to sort of bring this back to what we talked about with the Montreal Protocol, as you sort of saw with those graphs, right? The ozone layer hole was coming back in modern times, right? In the early 2000s. The reason for that is our friend nitrous oxide. The more we combust, the more we mismanage our agricultural fields, the more we destroy our ozone layer. So again, our friend nitrous oxide, while cool to study for people like me, it's a big pile of jerks. So we know this trend exists at the top, right? We know this 800,000 year record of perfect correlation almost between CO2 and our temperature. What does this mean for the planet? Well, this means that we're warmer, and we're warmer at a global level. Now, I like this map from NOAA for two reasons. The first is it's better than just telling you a statistic. It's one of the reasons, but it highlights a really important part of why we call it climate change and not global warming anymore. Now, this map, as you'll notice, 0 is in this kind of lighter colors like you see here. No change in temperature between 1990 and 2019. Blue means it's cooled by about a degree. Dark red or redder means it's warmed by about a degree. And what I love about this graph, really do, is that it shows you a key point of climate change is it's not uniform. Not every part of the planet is affected the same. Look at this planet. The Arctic is on fire, right? It's deep red. The Middle East, Africa, really red. The Australian outback, New England, unfortunately, the American Southwest, the Amazon rainforest, they're deep, deep red, but you'll see some places have cooled, right? This part of the Pacific, it's part of a gyre, has cooled. This part of the Antarctic down here has cooled. So the warming of the planet is not uniform. So some places say, like this part of the United States, right? The Dakotas, right? It's not seeing as severe effects of climate change at this point in time as say Alaska is, or here in New England. So climate change is not uniform, but the global trend is about a 1.02 in that ballpark, about 1.1 now, just as a note, change in global temperature from pre-industrial times. And it's not uniform, but notice that most of the planet is red, right? Most of the planet is red or orange or something. So globally, while some places have cooled off a tiny bit, we're seeing a monstrous increase, and it's not uniform. So keep that in the back of your mind. The rate at which climate change is happening has never been seen before, and it's happening at different rates across the planet. So let's talk about an important group of scientists. You guys might, depending on how much you pay attention to the news, you might have seen this group of scientists actually make the news earlier this week, or maybe over the weekend. I forget when it came out. This group is called the Intergovernmental Panel on Climate Change, or the IPCC. Now, this is a coalition of about 2,500 scientists. Some of the best climate scientists in the world are a part of the IPCC, and it spans 130 countries. And this is not just like scientists that study the atmosphere, or biologists or physicists. It's actually like economists and sociologists and lots of different types of scientists that come together to study climate change, because this is such a big deal. And so they do a couple things. You can read about the IPCC at their website if you'd like. It's linked here. But they study climate, they study the economics, they study the ecology, and they study the health impacts. They do this globally. And the other thing they do, which we're going to dive into, is actually the models to predict CO2 temperature. So let's look at this. So we have emissions from fossil fuels and cement. It's gigatons of CO2 equivalents per year. So it's gigaton is 10 to the 12 pounds. I'm sorry, 10 to the 12 tons. Sorry. So it's a lot. And then we have time on the x-axis. So the 80s, projecting out into 2100s. As you can see, it's 2100s. You'll notice that there's CO2 emissions, and there's a couple different scenarios. Now, this is like worst case scenario, where we just keep increasing dramatically over time in our CO2 emissions. This black line, or I don't know what color that is. This darker line here is actually just what we call business as usual, i.e. nothing changes. Our CO2 emissions stay relatively constant over time. And then we have a couple scenarios here where we drop CO2 emissions over time, right? Global pacts, Paris Climate Accord, so on and so forth. And you notice they all have different temperature, right? So if we dramatically increase our CO2, we expect to see up to 5 degrees warming. Business as usual, i.e. we don't try to tackle climate at all. We're talking about almost a 4-degree increase, but a bare minimum of 2. And then we see these other scenarios where they range between 1.7 to 3, or 0.9 to 2.3. So how much CO2 we emit going forward really will determine how much our planet's going to warm, and that shouldn't surprise you at this point. And this graph really shows you the same thing, right? But it's a much farther out protection. It's to the 2300s, where we look at just global surface temperature change, and you notice that the most extreme models, so this red line, which corresponds to this red line, as it extrapolates out into the 2300s, because remember, climate change won't stop once we stop emitting. It'll continue and continue for years and years and years. Projects really, really catastrophically high temperatures, plus 8 to 10 degrees centigrade. So it's no joke. So what's happening now because of climate change? That's sort of the next thing we're gonna tackle, right? What do we anticipate is going to happen with climate change? But first, we're actually going to take just a quick break. So it's 12:43. Let me just stop and pause. Got some stuff to talk about. So the rest of the class will be sort of about what's happening now because of climate change. And I don't know how close you guys pay attention to the news. I don't blame you if you don't pay any attention to the news, because it's, for lack of a better word, depressing as hell most of the time. So if you don't pay attention to the news, I would not be surprised. However, for those of you that pay attention to the news, know there's some pretty severe weather going around the planet, much more severe than there should be. So it's really, and I bring this up because it really ties back to this comic, right? The effects of climate change, while there's certainly in the future, there are signs of climate change happening now. The large forest fires in California, in Oregon and Washington, year after year after year, those aren't because of poor forage management. They're because the planet is getting hotter, because California is getting drier. The fires in Australia and the billion animals that died and the sad koalas and all that stuff, that was because of climate change. The extreme heat we've seen in the United States, in Europe, the extreme heat we see in the Middle East, that is climate change. That is what we expect to see. But before we sort of dive in, we're going to talk about all these things, but I want to just sort of lighten the mood because climate change is not the most fun thing to talk about. So I have a little piece of satire from my favorite TV show. For those of you that have never watched Futurama, it's from the creator of The Simpsons. It's a show set in the year 3000. So it's just it's a piece of satire about climate change as a whole. So we're just going to watch this minute video because I think you'll find it funny. And if you don't find it funny, know that I find it really funny. So that's why we're watching. So let's dive in because it's really accurate. So let's go.
Global warming, or none like it hot. You're probably wondering why your ice cream went away. Well, Susie, the culprit isn't foreigners, it's global warming.
Global wobble?
Yeah. Meet Mr. Sunbeam. He comes all the way from the sun to visit Earth.
Hello, Earth. Just popping in to brighten your day. La 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 la. And now I'll be on my way.
Not so fast, Sunbeam. We're greenhouse gases. You ain't going nowhere.
Oh, ah, oh, ah, oh, oh, God, it hurts.
Pretty soon, Earth is chock full of sunbeams. They're rotting corpses heating our atmosphere.
How do we get rid of the greenhouse gases?
Fortunately, our handsomest politicians came up with a cheap, last-minute way to combat global warming. Ever since 2063, we simply drop a giant ice cube into the ocean every now and then.
Just like Daddy puts in his drink every morning. And then he gets mad.
Of course, since the greenhouse gases are still building up, it takes more and more ice each time. Thus, solving the problem once and for all.
But
Once and for all!
So that's my little piece of satire for you guys. So accurate of how climate change works, right? I mean, this came out in like 2002, so it's still broadly called global warming there, but accurate, right? I mean, minus the cartoon aspect of it. But sort of, I mean, obviously the solution is wrong, right? You can't just drop a giant block of ice into the ocean and cool the planet. It simply doesn't work that way. But really, sort of shows you sort of a good satire of like how we've approached climate change as a problem, right? What sorts of solutions have we tried throwing at climate change? Which the Futurama should tell you that, given that it's just satire about the moment, it's basically nothing, right? So we've really tried nothing to meaningfully mitigate climate change at the global level. So given the accurate but satiric look at climate change, what does this mean, right? What are some of the effects on the planet around you? So the first thing we're going to start off is, what are the direct effects of CO2? Now, CO2 has a double effect. Now, CO2 is gas, so it dissolves in water. And CO2, when it's produced, also comes along with air pollution. So we're going to tackle both of those things first. So let's talk about what happens when CO2 dissolves in water. Now, whether it's the ocean, or whether it's a pond or a river or a lake, it doesn't matter. When CO2 is absorbed into water, it reacts with water to form a very, very weak acid called carbonic acid. So for those of you that like, say, beer, or you like soda or seltzer, those drinks which have carbonation to them simply means they have a lot of CO2 in them, which means they have a lot of CO2 in them, means they have a lot of carbonic acid in them. So sodas, beers, even wine to an extent, seltzers, they're all acidic because of this idea of CO2 dissolving into water, then reacting to form a very weak acid. Now, when you drink soda or beer or seltzer or anything that has acidity to it, that's bad for your teeth. I'm sure you guys probably have dentists that have told you don't drink soda because the sugar and the will rot your enamel. And yeah, CO2 is bad for your teeth. But when we think about this from an environmental standpoint, acidification of the oceans, i.e. more of CO2 dissolving into it, is actually pretty catastrophic. Like very catastrophic. So what's going on here? Well, as CO2 dissolves in the ocean, it does it a lot. Like just as a note of all the greenhouse of CO2 we've ever emitted, because of how large the ocean is, about 70% or so of all the CO2 we've ever emitted, I should say, has dissolved into the ocean. So the ocean has absorbed a crap ton of CO2. And so as it absorbs more and more CO2, it leads to some pretty awful things. Now, the first one we'll actually talk about is coral reefs. For those of you guys that have ever been to the tropics, you guys know coral reefs are awesome. There's these living organisms. Just to note, coral reefs, they look like rock, whether it's this type of coral, a brain coral, any type of corals, they look like rock. That's actually simply not true. They're living animals. So if you ever see anyone hurt a coral, like or try to draw their name on it, you slap them, because coral is living. It's a living organism. It's living tissue. It would be like carving your name in the side of a cow or your dog. That's the equivalent of drawing on a coral. So if you ever see anyone harm a coral, you smack them, because that's a bad thing. But corals, when they're subjected to slightly more acidic ocean water, they actually start to undergo a process called bleaching. So natural coral, it's all happy and it's colorful and it's got all sorts of stuff. But when coral bleaches, as we see in the Great Barrier Reef, or we see any of the great reefs across the planet, it's actually when the corals start to turn white. Now, corals are wild. They have this symbiosis going on. They have this organism that lives inside them called zooxanthellae. And what the coral does when it's stressed by changes of the acidity of the ocean, or sometimes by temperature, it will expel its symbiote, the zooxanthellae, becoming white. And so when coral is stressed, it will become bleached, i.e. it will lose its symbiote. If it loses its symbiote for long enough, it depends on how long depends on which species of coral it is, it eventually will die looking like this. So more CO2 means more acidic waters, which means bad things happen to our coral reefs. And so for those of you that have ever been to the Great Barrier Reef, I envy you, because it's for obviously what I've seen on documentaries and pictures, it's gorgeous, but the Great Barrier Reef suffers this year after year after year, bleaching events because of ocean acidification. We'll come back to coral reefs in a moment. But the other thing we actually see is the effect on our hard shell organisms. Now you might ask, what hard shell organisms are we talking about here? Well, there's a couple that we're interested in here. Now, the first is actually shelled organisms. So I have an example here of oysters. I don't know, I don't really like oysters, but a lot of people like oysters, and they're a very, very valuable piece of aquaculture. But you'll see that the normal pH of the ocean is here on the right. It's about 8.1. When the pH of the ocean is normal, the shells are nice and thick and darker, implying that they're healthy. But as you drop the pH of the ocean, you'll see the shells get whiter and whiter. It means they're getting thinner and thinner and thinner, making overall unhealthy oysters. Now we see that with oysters. We see that also with snails. Our snails here, nice happy shells down to fractured and broken and non-functioning shells. So you can imagine and this is under lower ocean pH. So you can imagine this does not support life, this supports life. So ocean acidification poses some serious problems. And then you can imagine like this is just a natural snail, so no big deal, but you can imagine how valuable fisheries are, right? How valuable an oyster fishery is, how valuable the lobster fishery is, the crab fishery. All the changes in the acidity of the ocean affects our hard shell creatures, snails, crabs, lobsters, oysters, mussels. And so you can imagine given the effects of ocean acidification, there would be some pretty severe financial losses to people who rely on aquaculture as a means of making a living. So not just biology effects, but also economic effects. Now, the other problem of more CO2, as I mentioned, is what comes along with CO2. And that's actually air pollution. As we combust coal, oil, natural gas, we produce air pollution. Why is that? Well, our fossil fuels are not clean. They contain other impurities. You guys probably remember when I talked about leaded gasoline, right? That's a type of pollutant that is associated with fossil fuels. And so fossil fuels are dirty. And as you combust them, you release those bad sort of chemicals that are found in our fossil fuels directly into the atmosphere. And so I like this little figure. We have the proportion of population affected here as the width, and then the severity of effects going up. So as you go up, it's more deadly, right? Death is obviously the most deadly part, right? And then the magnitude, i.e. the wider the base, means the more people it affects. And so something like death and ER visits and hospital visits and heart attacks are very, very serious, but they affect less people than, say, loss of school and work or doctor visits or respiratory symptoms, right? But they're significantly more severe. And I'm sure you guys probably know, especially here in a place like the United States, where our healthcare it's good, but extremely expensive. This is a huge economic, essentially, burden for not just the average everyday consumer, but you can also imagine it's a burden for our friends. Well, I'm not gonna say our friends, but the people that work in the healthcare business, right? Or Medicare and Medicaid, right? So air pollution is no joke. It's as a note, currently we lose about 9 to 10 million people globally every year just from the effects of air pollution. And that's the tippity top. So remember, it gets bigger and bigger and bigger as you go down. So there's not just health effects of air pollution, there's economic effects. So let's well, actually, let me get to that in a sec, but I just want to just sort of show you the health effects. So we can see particulate pollution here from the combustion of fossil fuels cuts on average about 1.8 years off of the average person's life. That's average over all 7 billion of us. So clearly some people get way higher and some people get way less. So you can imagine if you live in, say Los Angeles or Beijing that have really bad air quality, you can imagine particulate pollution has a much greater toll on your average life expectancy than, say, someone who lives, in Alaska, for instance. So, and the dichotomy here I actually like to point out is particulate pollution takes more time off your life than smoking and alcohol and drug use, which I always think is wild when you sort of think about it, right? Like how much of an effect particulate pollution has and how normalized it is as part of our society, whereas smoking takes less time off your life, but is much greater, at least here in the United States, is much more shunned as a public health risk. So some food for thought about how our life is affected by our friend air pollution. And then this sort of another graph from the World Health Organization. They say 7 million. The number was recently revised, but I couldn't find an updated graphic that looked nice like this one. But when this came out a few years ago, it was 7 million. As I mentioned, it's closer to 9 to 10 million now. But lots and lots of things, right? Pneumonias. So you can imagine people that, something like COVID, which causes essentially a type of pneumonia, right? It's exacerbated in places with higher air pollution, right? Strokes, heart disease, lung stuff, all sorts of nasty things are arising because of air pollution. And it's not just like on your health, right? There's economic effects from this, right? If you say work in construction and you have COPD from air pollution, you won't be able to work in construction anymore, right? So there's lots and lots of lost wages, lots of lost days, and lots of costs to our healthcare system, not just here, but also globally. And just to sort of show you some data from the Department of Commerce, so our own Department of Commerce. This is a little bit old data, but I like this graph because I can't find a more concise graph than this one from modern data. So this is from 2010, but it still applies today. Air pollution hasn't improved in the past 11 years, but you'll notice that across the United States, in 2010, we lost a staggering, 1,200 million working days due to air pollution. There again, 4,900 million restricted days and 630 million restricted working days across the United States. And you can imagine like how much economic impact that lost working days has on the economy. It's a lot. As we'll make mention of later in class, it's significant chunks of GDP. You're talking like 3% GDP across the country as large as the United States. So it's a big chunk of change. Yep, you had a question, Katarina?
So how does sorry, I was trying to phrase the question. The lost working days, like how does that work? Like is it just that like the like in California, like if there's too many wildfires, like it's not safe to go out to work, or how does that really happen?
Well, that's like an extreme example of it, right? So like you can think of like an extreme event, like a large fire in California that leads to like, I can't go to work because I can't walk, like I can't drive to work or something like that, right? That's like an extreme case. But the more common case we see is like people that live in the cities and get just like minor respiratory infections, right? You know, you can think of like minor respiratory infections, right? Minor, sicknesses, right? I feel short of breath, right? Those are the ones that really start to add up. Now, those crazy days, like where you can see the smoke from California in, say, Colorado, those are extreme, and they certainly contribute to this. But the big one is like, I just got a cold because I'm more susceptible to getting a cold because of more air pollution. That's what's really actually in play here. Now that you're certain your question is a good one, because clearly extreme events like that play a role, but it's actually the little things that add up, right? I don't know how much, if you guys have jobs or anything like that, but like I know, like when I was working in Boston, like at oh my goodness, I worked at Brugger's Bagels for a while, and I think there was like 30 or so people there, and every week I would get called to try to come in because someone was sick with a cold or a flu, or like it just lost work days add up. And you can imagine like how much that might add up if you're short staffed, right? You can't provide a product to people, right? Or you have to pay people's health, like your healthcare costs go up, right? There's all sorts of things that go along with the economic effects of lost working days. So that was a really good question. I really do appreciate it. So that's now, and then projections, clearly as we burn more and more fossil fuels, more air pollution, right? And so projections to the future don't look great either. And 2020 its numbers are higher too, right? So air pollution is not good. People that live in the city, as I mentioned, live significantly shorter lives, like 5 or so years, than people who live in, say, the countryside. So air pollution is not good, to say the least. So, all right. So more CO2 is bad for your air pollution and stuff like that. But remember, more CO2 means a warmer planet. So what are some of the effects of warmer ecosystems? Well, there's lots of effects, but one of the effects of warmer ecosystems is actually, we'll discuss, is our coral reefs. Now, coral reefs are globally on the decline. We've lost about half of our global coral reefs as of today. And we actually expect to lose coral reefs sometime within the next 10 to 20 years globally. Now, that might not seem like a big deal, right? You think, oh, the Great Barrier Reef's gone. That sucks. I couldn't go see it. But it is actually a really big deal. Coral reefs, as I sort of alluded to in the water class, are super vibrant ecosystems. They support a massive amount of living animal and other types of biomass. And so they are significant resources of biodiversity on this planet. So losing coral reefs is bad. But from an economic and human standpoint, about 2 billion people rely almost exclusively on the fish and other things that come from coral reefs or are influenced by coral reefs in some shape or form. So losing coral reefs impacts fisheries, it impacts people's capacity to feed themselves, and it impacts tourism and stuff like that. So losing biodiversity, remember, affects a lot of things, right? That $120 trillion price tag on nature, you damage that biodiversity like you do with losing coral reef, it's no good. Now, one of the other things we're seeing, and you guys probably have heard this one of some way, shape, or form, is rising seas, right? Sea level rise. Now, we'll talk about the 2 ways sea levels are rising in just a moment, but the big deal with sea level rise is simply water from our oceans are more able to make it into places it never could before. So just to show you what this looks like, we have days of coastal flooding. This is in Massachusetts. I pulled this right from mass.gov. They don't have an updated version of this, which always annoys me because they should, right? It should be 2015 to 2020, but they don't, which is stupid. Chippy! Chip! Lie down. Sorry, dog barking at nothing. And we have orange here. It's this climate-linked or climate-driven sea level rise causing coastal flooding. And then we have that would have occurred naturally. And you'll notice that from 1955 all the way up to the mid-90s, it's pretty evenly split, right? Climate change and natural coastal flooding are about equal. And then we start to get into the 1995 plus, and you'll see climate change induced coastal flooding is increasing. And in fact, during the time period of 2005 to 2014, it was the predominant reason why Massachusetts had coastal flooding. And what does coastal flooding look like in Massachusetts? Well, it takes a lot of shape and forms. Now, this is just actually a picture of my own. So for those of you that have never seen this before, this is actually Morrissey Boulevard. It connects, South Boston is down, up the road here. Quincy is down the road this way, right? So this is just in the middle of Dorchester. This is Dorchester Bay. There's a beach here. It's called Malibu Beach, and there's a little bay here as well. And this is the primary way to get basically from Quincy to Dorchester. But you'll notice the ocean's here, and the road is here, and the water from the ocean has intruded onto the ocean during a not so crazy winter storm. You can see there's not much snow on the ground at this point in time, but this small winter storm caused some pretty severe coastal flooding, leading to Morrissey Boulevard being shut down. I actually remember on this day, I don't know why I always remember this day, but I always remember this day because it took me like 2.5 hours to get to school. I was living in Quincy at the time. I had to take the train. It took me 2.5 hours on this one day, and I remember it because I came down here and I took this stupid picture. Anyways, but this is what coastal flooding looks like in Massachusetts. Now, this is just a road. This is just Morrissey Boulevard, and now it's an inconvenience to people, right? I mean, I have to go around, right? It's a long way around. Just as a note, if Morrissey Boulevard is closed, so it causes traffic. It causes people to be stressed, and there's all sorts of effects of coastal flooding. But the big thing with coastal flooding that does is it actually just damages infrastructure, right? This doesn't impact the road very much because it's just a minor intrusion of salt water. But you can imagine what would happen if we, say, had coastal flooding in the financial district in Boston, right, where there's skyscrapers, right? Or we had coastal flooding on very valuable real estate. So coastal flooding is no joke. So let's look at how sea levels have changed. So we have sea level change in centimeters. Again, centimeters, there's 2.5 centimeters per inch, if you just as a note, if you don't do centimeters very often, but you'll notice that sea level change, it's relative to the mean. So it's relative to the mean between 1990 and 2000, just as a note. Yes, I think that's what it is. I always forget this graph for some reason. It's 1990, 2000. Anyways, you'll see that our tidal gauges from our friends at NOAA are measuring sea level is increasing over time, eventually eclipsing the mean in 1990. And now based on satellite observations, we're actually, we're at close to 7 to 8 to 9 centimeters of sea level rise right now. Now, the number might not seem very big, right? 10 centimeters of sea level rise is about 5 inches. And you might say 5 inches is not that bad. But when you're thinking about a body of water as large as the ocean, remember 70% of our planet is ocean, a 5-inch or 10 centimeter increase in ocean levels is a huge amount of water. So don't be fooled in the small scale of this. That's a huge amount of water at the global level. It really, really is. So let's look at this globally. So I hate this map, but it's a really good map from NOAA. I hate it for one reason. I hate it because of the color. And so you can see a change in sea level here. Anytime you have a dot, it's a tide gauge, just as a note. Anytime it's red, we have a decrease in sea level, and anytime it's blue or darker blue, it's an increase in sea level. So for those of you that stare at graphs a lot, you'll know why this upsets me. It should be the opposite way, right? An increase in sea level should be red, and a decrease in sea level should be blue. That's why it makes me angry. But this is what we see globally, and you'll see pretty much the entire planet, sort of like the map I showed you about global temperatures, is mostly blue. A decent amount of it is white, but a lot of it is blue or very, very deeply blue. So we are seeing global sea levels rising. Now, there are some places that are getting more shallow. Not a lot of them, but there are some places that are slightly getting more shallow due to the currents in the ocean. But the one thing I'd like to highlight is actually here off the coast of the eastern seaboard of the United States. You'll notice that we're pretty dang dark blue here and blue throughout. These tide gauges kind of obscure that it's decently blue. throughout. And as a matter of fact, and this is of more interest to those of you that live on the eastern coast of the United States, normally, not just to go to school here, we're actually seeing some of the fastest rates of sea level rise here on the eastern seaboard of the United States than anywhere else on the planet. So Massachusetts, Virginia, Georgia, sea level rise is a big deal for us. So what's causing it? Well, there's two main effects that cause our global sea levels to increase. Now, this is sort of under the category of a warmer planet. So what is warming of a planet do to water? Well, the first thing it does is actually causes water to expand. It's kind of a cool thing. And you can actually do this as a little experiment on your own if you wanted. You could take a cup of water in a measuring cup, put it in a pot on your stove, and bring it to a boil. Not for too long, of course, because you'll eventually evaporate it out. And then take that pot of water and pour it right back into your cup, your one measuring cup. And you'll actually notice that the water will overflow the cup. Even though it's the exact same amount of water, it occupies a larger volume. So when water warms up, it gets bigger, right? So think about like cheese, right? When you melt cheese, you add heat to cheese, cheese goes from a block or a piece and it melts out, getting larger and larger. That's the same thing that happens with that water. Water expands when you heat it up. So that's thermal expansion. That's the red line here. And you'll notice that thermal expansion is increasing, but the biggest one is actually this blue line, which is added water or just melt water. Now, what does that mean? Well, it's this. It's scenarios like this. So this is the Peterson Glacier. It's in Alaska. You'll see this picture taken in 1917, so over 100 years ago. Really cool looking glacier, right? Glacier, all sorts of cool stuff. You see the mountain range in the back, right? They're identical images essentially. Fast forward to 2005, so less than 100 years later, you'll notice we have this nice little grassland. You see the glacier here still. So the glacier's still there to some extent, right? It would be about here. But you see that the glacier is pretty much gone. And so this is ice that's on land and is melting. And as we discussed, all water eventually makes it to the ocean. So we're seeing melting, large amounts of melting of our glaciers that are on our ice and glaciers that are on land. They're then flowing into the ocean, causing the levels of our oceans to rise. Now, the biggest source of ice is actually our friend Greenland, aptly named, because it's definitely green, right? No, Greenland's just a giant pile of ice, right? But Greenland is a giant piece of landlocked ice. So as Greenland melts, it adds tons and tons and tons of water to the ocean every year. And as the planet gets warmer, less of this ice hangs around. So our sea level goes up and up and up. And the important thing about this, I just want to make mention it, and people get confused about this quite a bit. Melting ice there's two problems with melting ice. We'll talk about the first one later, but it's how the albedo of the planet changes. That's one problem with melting ice. But the big problem is where the ice comes from. Melting of ice on land, i.e. glaciers in Greenland, of course, puts more water into the ocean. But the melting of ice that's already in the ocean, such as Antarctica, less of a big deal because that ice is already displacing its volume in the ocean, right? So you guys probably know if you have a cold glass of water, you got some ice cubes in there on a hot day, you leave it out in the sun for a couple minutes, all the ice cubes melt, the volume of your cup doesn't rise, right? Why? Because that ice already displaced its volume. But what does matter, if I took ice, say from Greenland, and I added it to my cup, my volume goes up, right? So that's what we're worried about. It's not Arctic ice that contributes to sea level rise, it's the melting of places like Greenland that really contribute to sea level rise. Now, I like to pick on Florida for a lot of reasons, but Florida is actually, Florida's easy pickings if you want to pick on a state in the United States for just as a note. But we talked about Florida earlier in the semester with our beautiful Everglades, remember, flowing from here all the way down to here. Now, Florida, like lots of the world, is very, very low lying relative to the ocean's level, and so the Florida in 2001 looks like this. It's Florida, right? Projections of sea level rise up into 2100 make Florida look like this, right? The entire Miami metropolitan area is gone, right? Huge parts of this very, very populous state are just completely submerged by seawater. So that's the sort of scenario we're thinking about. Higher seas means the ocean's just going to do what it wants. I'm sure you guys have been swimming in the ocean before and you got knocked over by a big wave, right? If the ocean wants to do something, it's kind of going to do it. And that's the same thing for our living situation. And then I like to show this one. it's I don't know. I'm not a big fan of. I like to show it because it kind of illustrates the problem on the eastern seaboard. But if we melted all glacial ice across the planet, this is the sort of scenario we would expect to see. Huge parts of the United States lost, Boston, New York, DC, completely submerged under oceanic water. So sea level rise is no joke of a problem, right? So let's talk about it in context of Boston, right? Because we're over here, right? But well, obviously we're not there, but normally we're somewhere over here on campus in Bentley and Waltham. So let's talk about Boston. What would Boston look like with climate change, right? What does Boston's sea levels look like? So if you guys have never heard of Boston's Climate Ready or Climate Ready Boston, take a peek at this boston.gov link here. It talks about all the science and the worries of the city of Boston due to climate change. And one of the things Boston is worried the most about is actually sea level rise. Now, Boston is not as low as Florida or say a place like Mumbai, but not Mumbai. I don't know why I said Mumbai. Thinking of a different city, like same place like Singapore. But Boston is relatively low. For those of you that don't know anything about the history of Boston, Boston was basically one giant salt marsh at one point. And we basically over time filled it in with dirt and stuff and changed it so it looks the way it does. So Boston is pretty low. And so we're worried about sea level rise, in particular because sea level rise, as I mentioned, is happening faster along the eastern seaboard than most places, eastern seaboard of the United States, than most places in the world. So, all right. So let's look at projections of the Boston 2070 high tide. This is not flooding. This is just what our high tide looks like. Where there's blue, that's where the high tide is expected to intrude. So you guys, for those of you guys that don't know, this is like where the aquarium is, right? This is like the financial district and stuff like that. So we're talking about significant high tides, not floods, just high tides in very, very valuable areas of the city, real estate wise, but also in very populous areas here in Chelsea and Winthrop and Revere, as well as in our airport to some extent, right? A huge part of our infrastructure. So that's the high tide. Now let's look at potentials for coastal flooding. Anytime you see greenish here, it's coastal flooding. And you'll notice that most of Boston is kind of blue. And with higher sea levels, when our coastal lines flood, as I show you with that picture of Morrissey Boulevard, the water is just going to go where it wants to. There's nothing really stopping it outside of a giant wall, right? And so that water is just going to penetrate deeper and deeper and deeper. So you're thinking about like seawater by the Boston Common, right? Because the Boston Common's about right here, right? Or sea level, in certain other places like deep, right? Jamaica Plain, Brookline, Cambridge and Somerville, right? Pretty steep coastal flooding due to storms, snowstorms, and the otherwise. And I'll be remiss if I didn't mention, this part like East Boston and the airport and stuff like that. So, and then finally, we have a triumvirate here where we have our coastal flooding, which is our greenish color, our high tides, which is our bluish color, and then we have social and economic vulnerability in these colors here. Now, what does that mean? Well, economic and social vulnerability means things like the disabled, the elderly, also typically characterizes it as communities that are largely of, like, say, minorities, like people of color, but also areas of Boston that are poorer. That's what the sort of the economic vulnerability part means. And you notice there's a pretty severe overlap of the blue and the green and the brightly colored areas. And what is the takeaway from this? Well, we'll talk about that. We'll talk about the idea later in the class, but the places that are going to hit hardest in Boston by sea level rise and problems in general are going to be the places that are already struggling, the places that are already not doing well economically, the places that have lots of elderly, and so on and so forth. So climate change is indiscriminate in terms of who it hurts, but clearly there's something not quite right in terms of the ethics behind climate change, which again, we'll talk about in a little bit. Now, one of the other cool things we're seeing with climate change, and this could be a class all on its own because it's really cool, at least for me, it's cool, is actually we expect to see more diseases. In particular, we actually expect to see more tropical diseases, more diseases carried by insects. The most deadly animal on this planet is actually the mosquito. I'm sure you guys probably know there's lots of terrible diseases that are carried by mosquitoes, malaria, triple E, Zika, and so on and so forth. The mosquito is arguably the most dangerous animal on the planet that's not named man, right? But the reality is insects, they respond really well to climate change, in particular insects that like wetter climates. And so mosquitoes, ticks, and similar insects that carry disease love climate change. Why is that? Well, if things get warmer, it means they can be active for longer. And if they could be active for longer, it means they have a greater chance of biting someone, a greater chance of picking up one of the terrible diseases they carry. And they also have more opportunity to produce more progeny, right? More young to carry more disease. So under climate change, we expect larger insect populations, which means more transmission of terrible diseases like malaria. But the other thing is, as climate gets warmer, as, say places like, Canada get warmer, or we think about like, places like Massachusetts or Pennsylvania getting warmer, it invites insects from the southern states to actually come into these areas that are experiencing warmer temperatures. Fun fact about the CDC, one of the most important groups of our government. I don't care what anyone says about the CDC, super duper important. But as you guys probably know, the CDC is established in Atlanta. Now, the CDC was established in Atlanta to fight one specific disease, and it kind of just hung around in Atlanta. It was actually established in Atlanta to fight malaria in the southern states. It was a big problem. Like, it was a really big problem back in the day. But malaria, as you guys probably know, doesn't really exist in the United States. But with climate change, we actually expect the mosquitoes to shift their range more northward, bringing malaria back to places like the American Southeast, and potentially malaria pushing into places like Pennsylvania, Washington, D.C., New Jersey, things like that. So we expect to see more disease-carrying insects and more insects in places like, that are colder. So not a good scene. Read a little bit more about this. I recommend the CDC link here. As I said, really fascinating idea. Could be its entire class all by itself, but I just wanted to make mention of it. Now, one of the other things we're seeing with climate change is our loss of water. Now, we know that as the weather gets warmer, it's going to lead to more evaporation from our lakes and rivers, which is going to lead to less water in certain places and more water in other places. So we can actually look at this, sort of this map from UNICEF. They're a pretty good source for water, because that's one of the things they tackle quite commonly. But we see that in 2005, we see the overall percentage of change in water withdrawal. It's relatively low across most of the United States, but it is red in certain places. But you see projections in 2060 of climate change going forward. You can see that the United States is expected to draw more and more and more water. And clearly, as you draw more and more water, it's not exactly the best thing, right? You start to lose your water resources, right? Especially as things get drier and drier. But we can sort of look at precipitation maps across the United States. What do we expect to see in 2050? Well, you see large parts of the United States are going to expect to get much, much wetter. But lots of the United States are expected, sorry, I'm trying to speak too fast, are expected to get much drier, right? Think about all the people that live in these areas, right? Expected to get drier. Now, dry is clearly a challenge, right? If you don't have enough drinking water, that's a bad thing. It's a bad thing, but too much water is also a bad thing. So I have a friend that does work in North and South Dakota on soybeans. I know that sounds really exciting, but one of the things they worry about in North and South Dakota is too much water. Too much rainwater is bad for agriculture as well. So too dry and too wet is not good. Not good at all. So it's kind of a fun thing. And then the other thing we're worried about is actually this process called desertification, i.e. the expansions of deserts. So going from areas like this with vegetation to barren areas like this. Now, the places we're concerned about this is actually places that already have deserts. So the American Southwest, the western part of Texas, the Gobi Desert, the Sahara Desert, and so on and so forth. We're worried about deserts expanding globally because of less water available in those areas. Remember, they're naturally already dry. With even warmer temperatures, they expect to be even drier, thus have less water and see the deserts expand. And so some of you that pay attention to the news in depth, I guess, might know that there's a handful of African nations trying to build essentially an emerald necklace at the bottom of the Sahara Desert to stop this process from happening. So they're trying to plant a crap ton of trees, like billions of trees along the bottom edge of the Sahara, to prevent this from happening. But it's a concern globally. And dryness is also a concern here in Massachusetts and everywhere in the United States. It really is. So this is from 2016, but this actually exact same map ironically enough, was the case in early May before we got all those deluge of rains here in Massachusetts. But you'll notice here in Massachusetts, 2016 or in 2017 or any year within the past decade, Massachusetts has experienced droughts, which you can sort of see reflective in like water bans and stuff like that. So droughts are a big deal everywhere. It's not just here, it's everywhere. And some places, again, are expected to see more precipitation, but by and large, we expect water troubles most places. Now, one of the things we're starting to observe is actually changes in nutritional value of our crops. So we know that warmer climates means less water, i.e. more water stress, which means you can grow less crops and less variety of crops. So you can only, when the planet gets really, really warm, or even slightly warm, there's only certain crops you can grow when it's warm and dry, which means you're limited in what you can grow, right? And that's not a good thing, not at all. And so when we think about that, like if I'm unable to grow, say, soybeans anymore, that's a huge sort of hit to a huge portion of the world. And so if we can grow less crop variety, that's not a huge deal here in the United States, where overconsumption is already one of our biggest concerns. But places like Africa and Central and South America and Southeast Asia that are already relatively impoverished, changes in their nutrition is not a good thing. And so let's look at some maps here, a map here in the United States where we're looking at agricultural yields. This is projected into 2080. And you'll notice that our breadbasket, this entire part of the United States where we grow the vast majority of our food, is expected to see significant declines in agricultural yields due to either too much rain or too little rain. And that, we sort of put this in perspective, like a state like Iowa, which grows, I think, about 13% of all of our soybeans, or a state like Michigan, which grows about 25% of all the legumes consumed in this country. That's a big change in food. And that's not just like a I'm hungry sort of problem. That's an economic problem, right? Given how important agriculture is to this area of our country. But you also see some places are expected to get more better with agriculture, right? Particularly this area and a little bit down here. But we expect to lose a lot of our agricultural output in the United States and globally as well. And then there's this final weird thing. So when scientists actually study the effects of more CO2 on our crops, they actually become less nutritious, which is kind of a weird thing. You can read a little bit about here, but I'll just give you sort of the cliff notes here, that when scientists grow crops under 2050 projections of CO2, crops lose 10% of their zinc, 5% of their iron, and 8% of their total protein content, which is a weird thing. It's just a change in the plant's like physiology that's driving these things. It's a weird thing. And again, not as a big deal here, right, where overconsumption is a big problem. But you think about, again, if I don't get as much energy or protein from my soybeans in Africa, well, that's kind of a big deal if you're already malnourished. So we're not in a good spot food-wise. But the other thing is, like, even luxury foods and drinks, for that matter, are expected to take a hit. So for those of you that drink coffee, which I'm sure is probably almost everyone, for those of you that drink beer, for those of you that drink wine, for those of you that like chocolate, all of those sort of, maybe I was going to say luxury items, but I don't think coffee is really a luxury item anymore. I think it's kind of a staple of society at this point. They're affected by climate change too. So we actually see pretty dramatic declines in the amount of hops we can produce, the amount of coffee beans we can produce, the amount of berries for wines we can produce, as well as the amount of beans for chocolate we can produce under future climate scenarios. So if you want to read a little bit about this, I linked this from insightclimatenews.org, pretty good site about how we're losing coffee biodiversity of coffee plants worldwide. And again, coffee's the example I give you, but I mentioned it's also beer, it's also wine, and it's also, I'm sure some of you like chocolate way more than I do, but chocolate is also threatened as well. So it's not just like my soybeans are troubling, it's things that are awesome in life, right? So lots and lots of stuff. Now, we've already sort of touched upon this a little bit, but we expect to see some changes in weather. Now we're seeing this right now, right? 130 plus degree temperatures in the Middle East, right? Scorching hot. So we expect to see some pretty dramatic changes in weather, but we also see some really interesting changes in our seasonality. So we actually see, relative to about 100 years ago, we actually see that growing seasons in North America, Canada, that's part of North America. North America and Europe, the growing seasons are actually sometimes up to 3 weeks longer across those two areas of the world, which is kind of a crazy thing to think about. Now, why is that? Well, just simply the planet is staying warmer longer. It's kind of a cool thing. You can sort of see this in this figure here. We see wheat growing now, and then projected places where you can grow wheat in 2050. Again, the expansion of and changes of seasons in these areas, which is a wild thing to think about. We also know, and sort of already alluded to it, we're seeing much wider droughts, right? And that's why we're seeing these massive fires in places like California and Australia and even Greece now. And we're also seeing much more intense droughts. And overall, and sort of the flip side of that is that we're actually seeing more storms. So as the planet warms, we have more evaporation of water from the oceans, leading to scenarios like this. Now, we're seeing less of an increase in the number of storms, though there is a slight statistical increase in the frequency of storms. The big concerning thing, which you can really take away from this graph, is this orange line here. We're actually seeing a pretty significant increase in category 4 and category 5 storms in recent years. And as you guys probably know, category 4 and 5 storms are no joke. They're category 5 have winds that top 200 miles an hour. They're super destructive. And so you can imagine, like, in a scenario where the planet is warmer, we expect to see more of these category 4 and 5 storms. And when we sort of think about the effects of storms, they're pretty profound, right? Look at how damaging Hurricane Sandy was to New York and New Jersey. Look how damaging Hurricane Harvey was to Houston. Look at Puerto Rico. It's still recovering for Hurricane Maria 5 years ago. So hurricanes are no joke in terms of how much they cost. And that cost doesn't just extend to like, oh, I have to rebuild buildings. But remember, people die in these things, and hurricanes are very destructive in terms of the tax they place on human life and our economic growth. And the other issue, and we've sort of already discussed this, so I won't harp on it for too long, but it's more drier areas which drive these large wildfires we see, right? Remember, it's not mismanagement of forests. It's not a thing, no matter who tells you that. It's just how dry things are getting. When things get super dry, as you guys probably know, they set on fire easy and fires spread easily. So more fires, again, we're seeing that all across the globe. So fires are no big deal. I'm sorry, are no joke. Of course, they're a big deal. Fires are no joke. And again, they're expected to be more common going forward. I feel like every year in California, the fire gets bigger and bigger and bigger. I feel like every year it's a new record for a fire in California, which is reflective of the changing climate. Now, we've sort of already make mention of range shifts of insects that carry diseases, but we're seeing some pretty strong shifts of insects that kill our crops and kill important valuable wild plants as well. So in particular, we're seeing an expansion of pests and invasive organisms. And so the example I'll give you here is actually the bark beetle. This is just kind of a nondescript looking beetle. I think it's cool because it looks kind of like a hedgehog. But what this bark beetle does is it lands on spruce trees. It lays its eggs in the spruce trees. And as you can see, its larvae chew through the bark of the center of the tree here and eventually kill the tree. But you can see the range of these organisms here in red. Relative. So the red is these bark beetles, and the spruce trees, which they like to kill, are in black. And that's in 2000. Projections of their range in 2080 basically encompass the entire range of the spruce tree. So this pest, which damages a valuable piece of timber that we harvest, certainly are expected to expand. And again, this is not just things that eat like trees, but it's also agricultural pests as well. Now, this brings us to our sort of our final topic about what are some of the effects of climate change on the planet. Now, this is probably the most serious aspect of climate change, not because of how damaging it is, but because of how what's the word I'm looking for here? Of how out of control it can make climate change get. And these are what we call climate feedback loops. Now, we'll talk about two of the most important ones. So let's dive into the first one, which is melting of ice. Now, it doesn't matter if it's the melting of sea ice or the melting of ice on our land, so our glaciers. But we do know globally we're losing oceanic ice and we're losing land-based ice. Now, why does ice matter? Well, remember, ice increases the albedo of the planet. It reflects more of the solar radiation back up into space, cooling the planet. So as we lose more and more ice, you can imagine that has a runaway effect. So what does this look like? Well, warming leads to melting of sea ice, which, as I've mentioned here, we're losing a lot of ice, which leads to more ocean being exposed, which, i.e. the albedo of the planet goes down, which leads to more sunlight being absorbed by the ocean or by the land, which leads to an increase in temperature of that area, which leads to more melting of ice, which leads to lowering of the albedo. And we repeat this process over and over again. So it's this really sort of sick cycle of we're doing one thing to the climate, and it's kicking us right back in the butt again and again and again. And it gets worse and worse and worse. So the more this pushes on this, the more this pushes on this and this. And again, it feedback loops into itself. So that's our first feedback loop. It's a really well understood one. It's accounted for pretty readily in most of our models about how climate is going to affect the planet. Now, the second feedback loop is actually the model I will just tell you we know so little about. It is so difficult to pinpoint the magnitude of effect this is going to have, but we know it's going to be bad. And the reason we know it's going to be bad is because Arctic permafrost, which is just permanently frozen dirt, stores hundreds of gigatons of CO2. Remember, we emit gigatons of CO2 per year. This is like hundreds of years of CO2 trapped in this permanently frozen dirt. So it's very much like the previous feedback loop we're going to see. We know, as I showed you from that graph, the Arctic is warming faster than anywhere else on the planet. Because the Arctic is warming faster, the temperature rises, leading to the permafrost becoming no longer being permafrost. It's just soil at that point. And permafrost, because it has lots of tasty carbon in it, the microbes wake up. They're hangry. They're probably not hangry, but they're definitely hungry. And as microbes eat all that tasty food in the soil that was permanently inaccessible to them because it was frozen, it releases lots of CO2. And more importantly, it releases a lot of methane, which, as we know, increases global temperatures. And as that happens, as the temperature rises, because more and more methane and CO2 are coming from the Arctic, it causes more of the dirt to thaw, leading to this happening again and again and again. And again, this is one of these terrible feedback loops where we poke on one end and it causes an unstoppable loop that we just simply cannot break the cycle of. As I mentioned, this is the part we don't know as much about. Most of our climate models from the 90s were really, really accurate, except for accounting for this. This part we just couldn't figure out. It's still really hard to figure out. It's hard to study microbes. It's hard to study the Arctic. But it is an important part of climate change going forward. And you can sort of see this in this picture. I love this picture where you have this frozen like piece of forest here. It got flooded and it froze. And you can see all these little bubbles and these large ones here. And what's going on there? Well, that's just gas from the permafrost that's now thawed underneath this ice, releasing methane and CO2. And you can physically see all the methane and CO2 being trapped in this ice. So again, this is a hard thing to understand, but we think it's going to be super important going forward with climate change. So that's all the effects of climate change, but let's talk about something that you guys probably think about, right? The economy, right? Dollar bills, y'all. So this is going to be one of the last things we talk about. We only got a few more slides to go through. But the costs of climate change are large. So I'm going to start with this quote from the Market Watch. You guys probably have heard of Market Watch. I mean, I'm not a businessy person. I even listen to Market Watch, or look at Market Watch. So you guys probably know exactly what Market Watch is. But 2018, they said climate change has cost the United States taxpayer more than $350 billion over the past decade, according to a report released last year from the Federal Watchdog Government Accountability Office. By 2050, that figure will be $35 billion per year. Costs include cleanup and disaster assistance from flooding and storms, which are set to increase under rising temperatures. So as I sort of mentioned with, say, like Hurricane Maria or Hurricane Harvey, there are direct effects on our infrastructure that we have to take care of. And that can be quite a large chunk of cash. Now, depending on who you ask for an economist, and it varies depending on who you ask, most economists give us a range of that costs per year of about $5 to $100 trillion by 2100, which is a pretty big range, but it's kind of hard to narrow down. The one thing I will say is that when they survey economists, about 96% say that climate change is the biggest issue facing economic growth going forward, and it's one thing that has to be acted upon now. I just figured I'd make mention of that. But you're talking about huge chunks of GDP globally being tossed away because of the effects of climate change. Now, we can put this in contrast to how much it would cost to reduce greenhouse gases, i.e. to stop climate change. And it's actually significantly less. So depending on who you ask, it's about 0.12 to 1% global GDP on a per year basis to fix climate change. But the cost of climate change is way, way higher than the cost of dealing with it. And just as a note, there was a study that came out recently that said for about $250 billion, if we restored all the soil across the planet, so we did what we did to the Florida Everglades, but just to all the soil, we could actually stop climate change within the next 5 years for $250 billion. But we'd have to take care of our soil, which we suck at doing. So that's probably not a feasible thing. So the costs of doing nothing about climate change are astronomical. The cost of fixing it, well, still pretty huge. Compare nothing to the cost that it will sort of impart on us on a year-to-year basis. And then the final thing I'll make mention of is a common talking point, is it will, fixing climate change will destroy jobs and it'll destroy the economy. It won't. The same way switching from the horse and buggy to the car or the train didn't destroy our economies as well. Shifting from, climate polluting jobs to climate safe jobs, around, conservation and stuff like that, actually are expected to grow jobs significantly. They did a recent analysis actually that found that depending on where you were, it was oftentimes a decent uptick, like a 5% or 10% uptick in GDP just from trying to tackle climate change. So the costs of not doing anything for climate change are astronomical. Just from a financial standpoint, there's clearly, ethical reasons to tackle climate change, but economically, climate change is a costly thing, and it's not super costly to do it. And the reality is it's going to have to happen eventually, because our fossil fuels, they're a finite resource, and so we're eventually going to have to make that switch. So why not make that switch and sort of stave off the worst effects of climate change? Now, other aspects of climate change on the financial markets include changes in tourism. No one wants to go to a place that's flooded, right, or destroyed. We know it has some pretty severe effects on infrastructure, as well as our real estate. And so the place we're seeing the most sea level rise is in this area, right? And so lots of valuable real estate exists. I don't know if you guys have ever looked at house prices on like Nantucket and Martha's Vineyard out here, but they're millions and millions of dollars. So you can imagine like this place that's super valuable for real estate, as the sea level rises, these are not so valuable anymore. So there's a huge amount of money to be lost on coastal properties alone. Now, we've talked about the effects of health and human productivity already, so I won't dive into those again. We've talked about agriculture as well, but in terms of the financial market, there's a lot of economists are worried about a couple things. Now, one of the big ones is price uncertainty. If you're relying on a good from, I don't know, say China, and climate change impacts that raw good or something, or it sort of deals a blow to our certainty around a price, which businesses like. We know insurance companies are worried about climate change, both from real estate insurance on houses, but also like human insurance on human lives and stuff like that. Damages to equipment, competition with other businesses, and this sort of kind of funky thing that I had never heard of till I made this slide, which is called stranded assets. And you guys probably have heard of it before, but like where you can't get an asset any longer. Like you have an oil derrick, it's trapped because you can't get it because of climate change. So the financial market is worried quite a bit. Like I said, it's a pretty high consensus of economists globally that climate change, well, it's not good for financial markets. So this brings us to the part of the talk which always frustrates me as a scientist is climate change denial. It's existed since climate change made it into the mainstream in the 90s. But the reality is climate change as a concept has been around, as I mentioned, for about 100 years now. And the scientific certainty around climate change and the effects climate change have on a scale of like 0 to 100 is close to 100. So when you do a survey of the scientific literature, which the IPCC has done, 98% of papers published show climate change is real and man-made. So there's simply no debate on the topic. The same way there's no debate on the topic of smoking causes cancer or vaccines are safe or any number of scientific uncertainties that have become politicized, there's no debate on climate change. Now, that doesn't stop it from being an identity both politically and sociologically, right? And same thing for any number of things, right, that are surrounding science. So when we think about those things, it's less based upon actual knowledge, right? If you follow the knowledge, climate change is real, right? If you follow the knowledge, vaccines are safe, right? Or the earth is round, right? Any number of things that people have converted into a belief or identity. So it is really a belief at this point. Now, why is that the case? Well, I mean, there's always people that are going to be conspiracy theory folks. Conspiracy theories are a really cool area of science. Just as a note, like from a studying them perspective, like psychology. But where does where does the hesitancy towards addressing climate change come from? Well, it comes from disinformation, right? You know, as our former president would say, it comes from fake news, but not like fake news in the way he talked about it, but actual misleading information on the effects of climate change and the realities of addressing climate change. And unsurprisingly, this comes pretty heavily from one industry that stands to benefit the most from denying climate change, which is our friends, the fossil fuel industry. So, you know, thinking about the Koch brothers, ExxonMobil, and so on and so forth. If you want to take a peek at about sort of how climate change denial works, this article from The Conversation is really fantastic. I won't talk about it too much, but just let you know what's really fueling this. And it's come to light recently in some pretty damning recordings, and as well as from our politicians' own mouths here in the United States and elsewhere. But misinformation has heavily influenced the conversation of climate change in this country and to an extent globally, but a lot so here in the United States. So, and as I sort of mentioned, it's a political problem, right? You can look at our politicians, whether it's our, you know, for those that live in Massachusetts, our Senator Elizabeth Warren. You know, I'm going to say something really crazy. I believe in science. Climate change is real. We have Bill Clinton walking away from Paris climate is a mistake. Bernie Sanders, Donald Trump is an idiot. I always like Bernie Sanders. I thought that was kind of funny. We see our friends, you know, Barack Obama. 97% of scientists agree climate change is real. We have Donald Trump spouting something that is clearly wrong, right? Global warming is created for the Chinese, right? That's simply not wrong. And then you have people like Stephen Colbert, and sort of like the video I showed you at the beginning of this part of the lecture, where they pick on a satirical way, right? Where they say, you know, Stephen Colbert, who's one of my favorite comedians, he has this awesome tweet from 2014 that says, global warming isn't real because I was cold today. Also great news, world hunger is over because I just ate. And really, it's a matter of perspective, right? You conform to the beliefs that are around you. If you live in an area that heavily denies climate change, and we sort of see this with COVID too, right? It's heavily low vaccination, like in say Alabama or Florida, you're going to likely conform to those beliefs. And also you're going to conform to the beliefs of the people you admire. If your favorite musician tells you when you're younger that vaccines cause SIDS or something stupid like that, you're likely to believe it, right? So we believe the people that are in charge, for better or worse, and we believe those around us. So climate change as an idea, there's no debate for it, but it exists for a variety of reasons. But regardless of what you believe, businesses are investing, and you'll see this all the time for commercials, in more environmentally sustainable practices. I see commercials on Hulu all the time for avocado mattresses and sustainable clothing and sustainable shoes and stuff like that. Businesses are going towards more environmentally sustainable practices. We know insurance companies are starting to increase rates, and they actually use the potential for sea level rise in their calculations on how much they're going to charge you for your homeowners insurance, which is kind of a wild thing to think about, but they're actually starting to factor it in. And we know lots and lots of companies, whether it's churches, universities, private investment funds, are diverting away from fossil fuel investments and trying to be more green about their investments. And we know that the United States military and militaries worldwide are taking climate change very, very seriously because it is threatened to pose a pretty severe national security risk. You can sort of read about this here from The Hill. It's a pretty cool little article, but you also might want to take a peek at this one from the Smithsonian, right? So part of the reason that Syria, as I'm sure you guys probably know this, but has that it still has, I should say, pretty severe civil war, is part of it's due to climate change induced water shortages and lots of people migrating, again, because of climate change induced water shortages. So it doesn't really discriminate. As I sort of mentioned, climate change is the issue of the day. It sort of overshadows all other issues we've talked about in this class because it affects every single aspect of your life: economics, the environment, food. It's also a moral issue, We'll talk more about environmental justice in our final class together, but the people that are most likely to suffer from climate change, places that are poorer, Southeast Asia, Africa, Central and South America, are likely to be hit the hardest by climate change. But they're the places, as I sort of showed you earlier, have emitted the least amount of greenhouse gases and continue to contribute the least to this problem. And one of the things we're actually worried about is not a relatively new term. It's existed for quite a bit, but it's climate refugees. As places become inhospitable, right? People are going to go to places where it's better. So I'm sure you guys probably remember all the fuss from like 3 years ago about the caravan of migrants coming up from the southern border to the U.S. border, right? I'm sure you guys probably heard of that. That actually turned out not to be true. The reality is, like, situations like that are what we worry about from a climate refugee standpoint. Large groups of people migrating potentially to the United States or other places because they simply can't live because climate change has made their places inhospitable in terms of growing food, getting fresh water, and so on and so forth. So it's a big ethical issue as well. And the other one, and this should piss you off the most, I hope it does, is there's an intergenerational equality problem here as well. It pisses me off a lot too. You guys are about 10 years younger than I am, but when you're in the generation after mine, but the people that are going to pay the price for this bill, the bill of climate change, is going to be my generation and your generation. We're going to live to see the worst effects of climate change. My wife and I are expecting a kid, and my son is going to see the worst effects of climate change when he's later in his life. But the reality is, the people that cause this problem and continue to push the rock, kick the can down the road, my parents' generation and Generation X, they'll be long dead before this actually becomes the serious problem. And so there's this huge problem of not just equality for the poorest areas of the world, but also from younger generations, that we have to pay the debt that our parents set up and have continued to not let us try to take care of. I mean, that's the reality of it, right? There's been tons and tons of bills that have gone to Congress to try to adjust climate change, and it's simply just blocked because of intergenerational issues. So that's the reality of climate change. Lots and lots of issues. So what can you do? Well, I mean, the reality is, one of the big things you can do is actually just reduce, change how you get your energy. I'm not telling you to go out and get solar panels or anything like that, but I don't have solar panels, but I get all my energy from wind and solar through my power company. So when you have the opportunity to do that as an adult, definitely do it. Or maybe just bug your parents to do it. It's basically almost the exact same price. I think I pay like a cent more per kilowatt hour than if I was getting my energy from fossil fuels here in Massachusetts. So definitely push your parents to do that. It cuts your greenhouse emissions by about 30 to 50%, depending on who you are. In turn, if you had a car, if you can have the chance to buy a car, if you can afford one, electric is always better, especially if you can power that electric car at your house that's running on clean energy. So those are the two big ones, right? But the other big one that you do individually is actually like your food, right? Trying to waste less food and trying to eat less, animals, right? That's the big one, right? Shifting away from animal protein to more plant protein. So there's lots of things you can do. You can buy carbon offsets, you can offset flights, you can donate to climate groups. There's lots of stuff you individually can do. But the reality of climate change is it's global, right? The biggest emitter of fossil fuels is China. It outpaces the entire G7 in its entirety per greenhouse gas emissions. So this is not a local problem, right? This is not like, oh, we have a plastic problem, we can solve it here in the United States. It's a global problem, and it's a tough global problem. But as I sort of showed you with the Montreal Protocol, we can fix global problems. And it's not overall that expensive. It just requires a commitment, a divestment away from life as usual. Because thinking about your choices is great, but you have to sort of put this in perspective. The way we sort of live, the vast majority of greenhouse gases can be traced to 100 companies like Amazon, ExxonMobil, large companies that we, with policy, can hold accountable, right? We could hold ExxonMobil accountable for all it does. I mean, don't get me wrong, it produces a product that we need right now, but we can still hold them accountable for those things. Same thing with Amazon, same thing for any large company. We can hold them accountable with policy. And that's the best way you tackle this problem, is with policy locally and globally, to hold people that pollute a lot, whether it's a large company or, for a matter of fact, some of the biggest polluters on the planet are not just Americans, but also the wealthy. A person like Bill Gates has about 140 times the greenhouse gas footprint than say you or I do. So holding people accountable, that's the best way you tackle climate change. And it's not just here in the United States, but holding our raw goods, the places we get our raw goods from in say like Africa or China, holding them accountable as well to try to fix this problem. So that's going to be the end. So what do we take away from this? Well, temperatures in modern times are higher than in the past 1,000 years. CO2 is higher than it's been within the past million years. And so we know those two things are linked. So, and where does more CO2 come from? Well, it comes from human activities, right? The Anthropocene, our effect on our climate is pretty stark. Now, climate change is not just a problem of the past, it is a problem of now, it's a problem of the future. And there's lots of things that climate change as a whole is really going to affect, right? As I sort of mentioned, it's every part of your life. Climate change really takes a foothold. And the reality is there's no debate of climate change. It's humans. And I don't want you to think that, one of the sort of things I want you to take away is that, like, don't let a large company, like say, we'll go with Amazon because Amazon's an easy company to make fun of because Jeff Bezos went into space with a rocket that looked like a penis. Don't let a company like Amazon try to pass the buck onto you as the consumer. What we need to do is hold large polluters in account with policy. So your vote, it matters, right? I mean, it might not think it does, but your vote as a young person tries to send a message of environmental equality, environmental issues. So I'd like to end with just a quote. I'm going to read part of it, and then you can read the rest of it on your own. It's a long quote. Now, I got this quote a number of years ago, and I've changed a little bit of it. There's a part that says, it says COVID at some point. I changed COVID. I added COVID in because it fit. But I got this little thing from actually another scientist. I was at a meeting for a society I belong to. It's called NEERS, N-E-E-R-S. So it's the New England Estuarine Ecological Research Society. It's a fancy way of saying they do research on the ocean. That's it. And so we had this really great speaker, and he gave this really fantastic talk. It was a long talk, but I asked for this part of his speech because it really sort of gets at the psychology and the sort of sociological and geopolitical aspects of climate change that we don't really get time to talk about today. So I'm going to read a little bit of it. It's a long thing, as you can see. It's quite a bit. I'm going to read a little bit and then jump to the end, and you can read the rest on your own. But we is the root of the problem. Humanity is created by degrees, a Gordian knot of incentives that no one person or even country has the ability to cut through. It's no individual or country, it's a system. No one governs the system. It is governed by webs of incentives acting across individuals, nations, corporations, which reward and have normalized the very actions that will accelerate the process of climate destruction. Every single person's standard of living in developed nations is built on the status quo that is running the planet. Elected leaders don't want to upset the status quo for fear of being ousted by the people. The people are either brainwashed by corporations, think whatever you want of that, into believing there's no problem, or otherwise pissed at corporations, but relatively helpless to do anything about it. No one leader or corporation is going to do the selfless thing. It's a tragedy of the common situation. Guys know about that one. They all take advantage of the situation because everyone else is. Every country worries that if they reduce emissions, they have no guarantee that any other country will. No other country will make a difference alone, or there's no guarantee that any other rival country will simply increase their emissions and gain an economic or military advantage over the rival. I'm going to skip here. Is there hope? There is always hope, always. What will the shape take? Who can say? What can be said is that even when the possibility of hope is asymptomatically zero, there's a cause to act without hope. You play the game until the last moment, because even if victory is slim, it is guaranteed if you stop playing the game. Norman Borlaug is a name we don't hear often enough, which is funny because Norman Borlaug saved potentially billions of lives. About 100 years ago, Norman invented a species of high-wheeled yeet. This gave countries with little access to food the ability to suddenly produce enough to save billions from death by starvation. Who could you be? You don't need to be any sort of genius to potentially create by design or by accident something that changes the course of our history. Because I articulate the problem, people ask me for the solution. I don't know the solution, but you might. More accurately, all of us do. And our collective imagination is the capacity to bend the universe itself. I can't fathom what that would look like. Maybe you don't find the solution, but maybe you, in your efforts, and unknown to you, inspire the one or ones who do. The sun is low, the time is short, the cataclysm is here, darkness surrounds. little overly poetic, but it is what it is. But life was born in primordial earth of fire and lightning and endless turmoil. In that chaos, life was born. And so long as we exist, there is hope that we can persist. And so one of the things that climate change, the people dislike the most about climate change is how doom and gloom it is, as you know, as are many things in this class that we talk about. But the reality is there's always hope that we can change. There's always hope that we can do better, but it starts with making that action. So this last slide, it's for you guys. There's some really nice links from a bunch of different places, you know, NASA, IPCC, and so on. Just really nice little thing. I found on the internet a couple years ago. I've just been putting at the end of my slides because it's a really great source of links that you could sort of taking a peek of some of the things that are controversial, how we can potentially act and change things, whether it's a carbon tax, which people agree is going to be the best way to actually fix climate change, even though most conservative lawmakers hate it, as they hate most tax, and better lobbying. You know, everyone does it, so might as well do it for for more just causes like fixing climate change. So I definitely recommend that you take a peek at this quote. It's a really powerful. It's long, which I didn't want to dive into it. So you guys have listened to me talk enough. So definitely read it. Definitely take a peek at some of these links. Become as knowledgeable as you can about the topic because it's not going away. And it's a topic that bears fighting for. Doom should never set in about any problem, right? We've talked about plastic and the tons and tons of plastic there is. Doom should never set in for that problem, or biodiversity loss, because as we've seen time and time again, like humans do great things, right? We fixed the Everglades, well, sort of, right? We eradicated smallpox, right? We developed a vaccine for an unknown virus pretty much in 8 months, right? There's no limit to what we can do. And so I recommend that you do become as knowledgeable as you can about this problem, because again, it's the problem. Might not be the most fun problem to learn about, but it is the problem on the planet. And as I hope I've sort of conveyed to you, there's no aspect of this planet that climate change doesn't touch. If you don't ever see yourself being involved in anything environmentally related, it's still going to affect you in some way, shape, or form, either personally, economically, or in your career. So like I said, I definitely recommend reading as much climate change as you can, become knowledgeable, bug me with questions, because again, it's the issue. Like it is the issue. So, but with that, I'm going to stop recording because I've been talking for way